Good morning, everybody, to PyCon 2013. First day, first tutorial of the day. So we're going to start with faster Python programs through optimization. It's very nice, the room is pretty much filled. A lot of people are interested in faster Python programs. Just a few announcements. Please, when you come in, sign in there and take a handout. And also, I will show it again. There's a web page with some instructions to set up things. I will show you the link after a while again. So try to set up things for a while. Okay, we're going to have 3 hours to go through this topic. Everybody of you should have a handout. It's 84 pages, quite a bit. It's a pretty comprehensive handout. And we're going to go through this tutorial. First of all, I would like to introduce myself. My name is Mike Müller. Down here you see my name and my email address. If anything is wrong, you can send me an email. And I've been teaching tutorials at PyCon US since 2007. So that's my tutorial number 13. So I have quite a record on teaching tutorials here. And also I teach quite a little bit of Python. You see this logo here, Python Academy. That's my company. And I've been teaching Python for now 7 years. And that's pretty the main thing I'm doing, teaching Python, besides some programming. So if you're interested in Python courses, you can ask me. I also have a booth at the expo hall, so if you want to talk to me, you can always find me at the booth and talk to me later on. So enough plug, let's get started. So I've been using Python since 1999, so it's quite a while, and it's my main programming language ever since, and I started teaching in 2004, so it's like quite a bit, and I just made some statistics, like I have like 280 days or 88 days teaching Python so far. That's quite a bit. Okay, that's about me. And I would like to get a little bit about you. I just want to get some background about your Python experience to know what I can expect. So please raise your hand. Who has less than 1 year of Python programming experience? Few people. Less than 2? Less than 5? Okay, that's more than 5. So that's about half the people have more than 5, something like this. So it's pretty mixed, a few beginners and a few more advanced people about it. So this topic is about faster Python programs. This is a very big topic. I gave this tutorial several times. It has some through iterations. And first, let me introduce the topic a little bit. After this, we're going to start doing some interactive work so you can work along. So just let's go to the table of content. First, I have to give you some introduction and some guidelines, and then we start with some tooling things, strategy. And the strategy has some source code inside, so we see what kind of things we can do to measure things. Measuring is a very important thing. You can see we spend most of the time measuring something. And then we're going to dive into a little bit algorithms and anti-patterns, some things you should do or should not do in Python, some background, and we have a few examples. It's a selection. There's more, but we don't have so much time, so this is some selection, some impressive ones. Then we look at some data structures, which are interesting. So data structures and algorithms are very closely related. Some data structures you can use, so you get a lot of algorithm for free in Python if you use a data structure. You should take advantage of this one. Then we have some technique. Caching is a technique to make things faster. Then we go into some computational expensive example, and then we have another speed testing thing here, and then we have different versions how to write this in pure Python, and then we look at some techniques how to make it faster, like using Psycho, which is a little bit outdated, but still there if you have a Python version, and PyPy a little bit, and we look at NumPy, and we also look at multiple CPUs with multiprocessing. We combine everything. And in the end, they have a compilation of tools. So it's quite a bit a program. As you see, the number of pages is pretty high. And therefore, usually I teach this as a one-day course, so there are some exercises, but we don't have time to get into the exercises, only 3 hours. But I want to give you some more or less comprehensive overview over the field. So you could do more, like have a day extensions. If you do extensions in C, that's a whole new other field, so we don't go into extensions here, which is also some kind of optimization technique. And there's more to it. There can be more. There's a lot more tools out there, but I selected a few where I think they're important. You can find a bunch of others which are similar in scope, but you have to make a selection somewhere. Okay, let's get started. I will talk a few minutes. So everybody says Python is slow. Actually, it's not really true. Depends what you're doing. Python can be pretty fast. So if you do string processing, stuff like this, Python is pretty good, I have to say. There's a few things Python is really slow. Numerics is one of the examples, but there are some tools. We can look at a little bit numerical calculations. They can speed up Python orders of magnitude sometimes using some interesting tools. And first of all, I want to argue a little bit against optimization. So don't optimize too early, because there's the saying premature optimization is the root of all evil. So optimization can have some drawbacks, some disadvantages. Can make your things more difficult to read, and you might not get so much out of it as you think. So, and this is I wrote down. I just want to go through this quickly. First of all, we have to make a case. You really have a case. Things are too slow. Yeah, that's not that easy. So we spend quite a bit of time on measuring. So you have to measure things. If you don't measure, you don't know what you're doing. Guessing is wrong most of the time. So even I have a bit of experience, and I guess the reason, and then I measure, and I'm wrong. In the aftermath, you think about it, it's clear why you're wrong, but from the beginning, if you have some gut feeling, you might be pretty wrong. And you have to make a real case that you need the performance. And then also figure out if it's really Python that's a reason for things being slow. Especially don't optimize as you go. So first you have to make this thing work right. If you make it right, and then if you have some tests and stuff like this, then you can make it work fast if necessary. And also use only realistic use cases. If it's an application that's used only for one user, you don't have to test like 10,000 concurrent users on the thing. That can be an academic exercise, but for practical purposes, usually it's not needed. Architecture is also a part of like a higher level algorithm. So how you set up things in the big picture. That might be some courses that make things slow, not the programming language per se, but how you set things up. Sometimes there are bugs. Yeah, people forget to sleep in the inner loop or stuff like this, and things are slow. Those kind of things to make it work right first. And it's really too slow. Very often, not the whole program is slow, but only small parts of the program. We can look at it with profiling. So with profiling is very important. That's one of the big tools. You profile and see if things are too slow. And also, we also have to make sure that after optimization, the program is producing the same results as before. So the best thing is obviously you have tests, automated tests, and you run through, and as you do something goes wrong, the test will tell you immediately. That's something important. Okay, and there might be a lot of reasons why your program is slow. It doesn't have to be Python per se. If you have a program that works with a network, then network's connections can be slow. If you work with a database, a lot of programs that work with databases, the database is the bottleneck. Very often, input-output can be the bottleneck. You call the system, you call out of the system, then not Python is the program, but the system calls doing something. So you can optimize your Python, whatever you want. If you have to wait, it doesn't matter if you wait slowly or wait fast, you still have to wait. And you won't get any faster if you make the Python faster if you're waiting for some system calls and things like this. There's some literature here, some books. They have something, and I used a few examples from these books. You see here the cookbook has something, new cookbooks coming out soon. They have some pages here about optimization things built in. Okay, let's get started. So everybody should have, again, I mentioned it again, go to the website, download the examples. So if you go to this website, that's a URL again. So PyCon 2013 Community Tutorials 24. Download the source code, and then there's a few things to install. I decided to use the IPython notebook for part of the teaching because it's a very nice tool to do things. So even if you don't have it installed, it doesn't matter. It's just for me to show you. But if you have it, it's a nice way. IPython notebook. It's IPython, and if you start IPython here, if you start IPython with notebook, this line here, if you have IPython notebook installed, then the browser will open and we'll go to the URL, and then you get a notebook. And this is very similar, but if you know Mathematica notebooks. And this is very nice. It's a mixture between interactive shell and some document. So everything is stored here saved in a document, but also I can work interactively. It's a mixture. So that makes it easy for me to explain things. Okay, first of all, we want to measure how fast things are. Measuring is a big part of the tutorial. We'll see measuring all over the place, and I will cover some basics about measuring first. The first topic is profiling CPU. So if a program is too slow, actually we have two focus points: the CPU, so the calculations, whatever you calculate is too slow, or memory usage is the other topic. We're going to look at the memory usage, also some examples how to minimize memory usage, or at least measure memory usage to see what's going on. Python comes with a module test, and this test module has a PyStone. Actually, the package test has a PyStone module in there, and then you can measure how fast your computer is. So if you do this, if you say from test import PyStone, then you can call PyStone PyStones, and you get back a result, and this is the runtime of this thing and how many PyStones you get. So I have 61 or 62,000 PyStones. If you do this for different types of Python versions, you can also run it from the command line. There, in lib test, there's a PyStone module. So if you run this for different kind of Python versions, you can see here I have a 2.5, 2.6, 2.7, PyPy, and so on, or 3. You can run it. You will get different measures, and you will see there's quite a bit differences here. The PyPy is significantly faster than CPython. And IronPython is also faster, JSON is slower. So if you use different Python implementations, you will see different results. And this is important. We'll use it so we can see if you have an algorithm how fast it is, and we can kind of scale it somehow to the Python implementation and the hardware you're going to use. Of course, you will have different numbers. If you have a different machine, you will see different numbers. That's the first thing to get some feeling about the PyStones, and I wrote down some measurements about PyStones. Okay, let's go measuring here. I have a file that's actually converting PyStones. Because PyStones is a big number, I convert them to kilo PyStones, dividing them by 1,000. I have a small helper that's doing this. So if you look inside, here in the measuring, if I'm in subdirectory measuring, there's a file PyStone converter, and if you look inside, it looks like this. And it's not very interesting. It's just doing this PyStone here, and then it just converts, takes the times of seconds, converts by the PyStones. I calculate up here and divide it by 1,000, so the number's not so gigantic, and makes it easier to work with. So if you do this, you can run this program. It's a small helper program. The test should run here if you run it. So if you just say Python and run the PyStone converter, then you should get some output like this. And you see the seconds and the PyStones. And this is kind of a mapping between time and PyStones. And then you can you can compare different kind of Python implementations if you have this kind of very simple mapping. Okay. Let's start with the first topic, profiling. So, as I said, if you guess about performance, 90% of the time you're wrong. You have to go and measure and then figure out what's going on. Even if you have a trivial program, you might be wrong, and if the program gets more complex, you're even more off. So let's look at some things what you can use for profiling. So if you look in your handout, I listed a few things you can use for profiling. There are several tools. And Python comes with profile, which is written in Python itself. It's rather slow and has impact. The problem is with measuring, if you measure something, you always change the system. There's no way out of it. So as soon as you start measuring, you influence the system. It's just a question how much you influence it. So if you influence the system by 200%, it's probably not very good because you're kind of screwing the measurements. If it's just a few percent, it's fine. There are two other tools, Hotshot and cProfile. This. So let's look at some examples. So if you go in this interactive thing, I put it here so make it a little bit faster. So if you say interactively import cProfile, then you can start profiling things immediately. See, I import a file called profile.me, and this is just a small example file I would like to use to profile things. So if let's just show you the file. So if you open the file profile.me.py, then you should see this file. And this is not very sophisticated, it's very simple. But just, you always want to have the simplest case that makes your point. And they have two functions, this fast function, this slow function. And this is doing nothing else but sleep. You see, I import time from the standard library, and then I sleep. And here I sleep 1,000th of a second, here I sleep 1/10th of a second. So there's 2 orders of magnitude difference here. That's all that is. And then I have 2 other functions that use this function. You just have a loop, and doing it 100 times, calling this other function. That's all they're doing, and I run them. So if you run them, then you see that the other function probably takes about 100 times as long, because most of the time is spent in sleep. This is pretty obvious here, though that's good because we know what to expect, and now you see if you profile what's coming out. So if you profile now, you see now I can use my interactive thing. So you can, if you don't get IPython installed quickly, then you can always use the normal interactive prompt to do this. Should be works the same. You just import profile me, hit this go to the directory, import this one, and then you make an instance of the profiler. So I make now actually if I press Shift Enter here, I make an instance. I execute this code, and I made an you see the number changed here now. I'm 171. And I made an instance of this profile. Profile is a class. I make an instance, and now I can use this instance in several ways. This one can do a lot. I want to show you some basic usage. And now I can go, profile me is a module. Remember, that's a module. That's a function. And I just say run call profile, and I run this function. And this is running in the background. And then I can call run stats, and you should see something like this. So if you say run stats, you would have a result like this. And you get some simple result. Our model is very small, very few functions, that's why it's very short. If you have a more substantial program, a more realistic program, this list will be much longer, obviously. And then you see some statistics about the things. You see I have 202 function calls in 0.1 seconds about. And then you have this table, and there's a few things listed. So n calls obviously is the number of calls you have there. Then you have the total time to spend in this function, then the time per call, which is too short to show here, so it's fast. It was rounded to this 1,000th of a second here, so it's shorter, that you don't see 0. And then you have a cumulative time for this calls here, and the time per call. So there are some statistics here you can see, and you can see most of the time actually is spent in this sleep here. If you look at this time here, then that's pretty much corresponds with the cumulative time here. So most of the time is spent in the sleep. The other ones are so short that it doesn't matter compared with this one. So and if you do the same thing, so we make another instance of our profile class, and now we use a slow function here, and then we say print stats. And if you say print stats, you call this, then you will see the results for this other one. You see the runtime here, it's about 0.1 second. That's what we put in. So if you calculate 1,000th of a second times 100 is pretty much 0.1 second, and the rest is overhead for the calls. So the big majority of the time is spent into sleep, and here we are about at 10 seconds, and a little bit remainder, which is all the calling. So the 10 seconds waiting is there, and you will see this reflected here. Then you can see the 10 seconds where they come from, and see this function called the sleep in total takes 10 seconds. And all the rest just takes very little time to add here. So the function calls are much faster compared to the sleep. So this is very obvious. You can see the sleep is eating your time. So, and then this statistics module, the stats, provides you several opportunities to sort the data. Because now you look at it, and sometimes you can sort them in different ways. And this is easy to be done. So before sorting, there's another way to use it. You can here I use a function object. That's a function object. So everything's object in Python. So I just throw in the object, and here I do a different thing. I throw in a string, and this thing is evaluating a string. So this is a different use case, and I just throw in the string, and it's evaluating the string as it is. So you can produce the string automatically. And so if you want to profile things automatically, this might be useful at times because it's just evaluating the string, and you can do this. But the result should be the same. You see, it's pretty much the same, just the last digit is different. This is just the measuring accuracy. It's a little bit different, but if you look at the times, it should be the same thing. Yeah? And what you can do, you can also store all the results in files. So if you supply as a second argument a file, I use the stats extension, which is not necessary, but it's common. Then the results are stored in a file, and then you can post-mortem analyze the results in a file. That's very often what we're doing. So we run it and store everything in a file. So if sometimes the things take long, it might take an hour to run the test, yeah, and then you don't want to run it over and over again. You just want to store things and then start analyzing, look at things in different kind of ways, and that's what we're doing here. And once you have done this, there's different ways to look at the data. We look at the standard library has a pstats module. The pstats module allows you to do simple analysis and rearranging this table with the results and look at different things. And the other one would be some graphical tools. There are several graphical tools, and we're going to look at one, which is called Run Snake Run, which is very nice, and you have some graphical impression how things are going to look like. Yeah, so if you have this pstats module as we have here, you just run this pstats here. And now you see I use this file. The fast one in this case, this is just, I just have relative path, that is just store the file. So if I do this, if I run this one, then it stores the files right in the directory where I am. So I'm in this directory, so if I go up and see I started the IPython from this directory, and there's this stats files. You see the stats files that I just produced, and they end up here. This is the IPython notebook, by the way. This is just the document I'm working in. Yeah, and relative to this, I have stored this stats file. And if you look inside, it's a binary file. You won't see a lot, but there's programs that can make use of the data. So we have this thing in 2 steps. First, we store all the information, and then we can read it back. And then we can read back as often as you want, and it's much faster than rerunning the test, which can be potentially slow. This test takes 10 seconds to run, and reading a file, it's just you don't feel it's there already because it's so fast. And then if you do this, you read this file, and then you print the stats. So if you do this, like I've executed thing here now, you see it's printing the stats. You see now the numbers going up. And then you see it's doing the same thing we had before interactively now, but we can do it much later. So you could run a bunch of tests and store the results in files and then run it. You see the numbers very similar. It's just the last digit is a bit different. What comes out of it, and you can look at these things. And now, once you have this, now you can. That's a return value, by the way, here. And then we can do different kind of sorting. So you have all kind of ways to sort things. So sometimes you're interested how many times a function is called. Sometimes you're more interested in the runtime, or sometimes you're interested in other things. And this stats here takes different arguments, and you can sort this ones. And I sorted by time. You see, now it's sorted that the one that takes the most time is first. Here, that's the same sorting as I had here, actually. That's a default sorting. You can sort by time. And you can also, for instance, look at the callers. You see, I say now print starts callers from fast, and then it prints the callers. So I see which function is calling which one. So I have this is very simple. It's a very simple program. It's just four functions. If you have a bigger program and use a lot of standard library modules, you have a lot of calls going on. Here, it's just a few, but you see which one is calling which one. So you have this. And actually, there are some other tools which I'm not showing here. They create a graphical representation who's calling whom and what's going on. And this can be very, very instructive. So sometimes you see, why is this calling? It's not supposed to call, and then you might find some kind of bug that makes your program slow because you have some unnecessary calls or something, which is not that obvious if you look at the code very often. So if it's a bigger code base, especially if it's not your own code, then you might not see this immediately. But if you look at the graph, it might be more obvious. Not necessarily, but could be. Sometimes graphs, they look so messy, they don't help, but in other cases they might be useful. So you can get this, see, you have the callers and you have the colleagues. So from both directions you can find out who is calling whom and what's going on. Yeah, so, and then you have total calls that tells you about total calls. Okay, this stats module you can do, but as I said, a picture is worth 1,000 words, so you can visualize the things. So this is some basic things. If you read through the documentation, you will find some more sorting possibilities, but you can always look at things with some graphical tools, and one graphical tool that's very nice is Run Snake, or Run Snake. So run. So if you just call run, if it's installed properly, you can use Run Snake, and you can look at a file. Just the file we produced before, this is the binary file with all the information. You can feed it into as a command line argument into this Run Snake program, or You can open it later in this menu if you like, and then you can look at the results, what's coming out of there. So if I do this, and everything's stored, it has a few dependencies, because you need WX and also need some other libraries to do this. You get a graph like this. So it's built off the screen here, so hopefully I can, yeah, okay now. See, now this is a very simple program, and you see it's showing you squares where runtime is. And it's very obvious that the big majority of the time is spent in this time-sleep function. That's a time-sleep function here. So this table is pretty much what we saw before, but you see now if I go here, it's just updating all these graphs, it's flickering a little bit. And you can look in here, and of course, I didn't test this with this resolution. There's more down here. If you select some of these here, then you can look at this table down here and you should see it. But I don't know how to move this here. So it just gives you the same, some more detailed information about these functions. And you see now it's very obvious that this function takes most of the runtime. There's no problem doing this, and you can look at it. So later on we're going to use a tool called NumPy, which is doing a lot of other things behind the scene. If you look at it, it looks much more complicated. Then you see that that's not that easy. So this is pretty obvious. If you have one big square, then you know you have to put the energy on this square and make it faster. If you have 100 small ones, they're all the same size, that's much harder, because there's no real basic one-time thing you can solve things. But this helps you, it gives you a nice overview. There are other nicer tools that have nice 3D stuff like this, but this is pretty good. That gives you a lot of information what's going on, and you see if you have a case or not to do optimization and where to start. So, and you'll see if you change something, you run this repeatedly, you will see how things are going to change and how things work out. Okay, this is a C profile. So everything, this is based on C profile, so everything it's in the standard library except this graphical tool, but this graphical tool doesn't produce any new profiling data, it just gives you a nicer view and some more information. There's also a way to get deeper inside, because C profile can only give you information about the function level. So it can tell you which function is slow, which function is fast, but it cannot go inside a function. And especially if you call out to extension modules, then this call to the extension module might be very slow, might take a lot of time, but you don't see it. If you have several calls of the extension module in one function, you see just this function, you don't know which call is slow. So you would need to rewrite your whole program that every call is in one Python function, which can be a lot of work, and sometimes not very feasible, because then you have already to move the variables around, stuff like this. Might be a lot of work, and you might have to undo it because you don't want this. For this one, there's a tool called Line Profiler. So if you have Line Profiler installed, I close this one here. So I go to I go back to my tutorial. So this, if you downloaded this, then this folder is called optimization here with my name, and then there's a subdirectory measuring where we have all the data in. This is those things we have in here, and now I would like to use Line Profile. It's by a module written by Robert Kern. And then once you have installed it, pip install Line Profiler should give you this software. And then we can use kernprof. The name is kernprof.py, and with the V option it shows you the interactive output. And now we can run our profile me through here. And this one, if we run it like this, it doesn't do anything special. So it doesn't do anything special, it's just using C profile and runs 3 profile. That will take about 10 seconds because we have this 10-second function there. And this output, so I make this bigger. You see this output is pretty much the output of C profile. What you get. Looks very familiar, doesn't it? I just have more function calls because I call both of them, so 400 function calls here. So now you can fortify your source code a little bit and make it use some decorator to profile things. So if I do this, let's look at the this file that's called profile me use line profiler. Short name. Okay, this is just this exactly the same module, and we put a decorator here. Decorators are very nice things to put those what's called cross-cutting concerns. So measuring the performance is a cross-cutting concern. You can put this in, and this just if you import, if you put it in, then and run it through this line profiler, then the line profiler will use it. If you want to run your program without the line profiler, you just define your own decorator profile that does do nothing. It just returns the original function and you turn it off. So that's a very easy way to turn it off. And doesn't have any overhead because it only happens once at compile time when Python is reading this in, and then there's no overhead per call if you just return the original function. There's nothing special here, so you can always turn it off very easily. And you put this profile in, and then once you do this, then that's if you run it under the supervision of this line profiler, it will go in and give you a line-by-line output what's going on with your program. So if you say current prof minus v minus l, minus l, and then this long file we just looked at, and then it takes a while. The disadvantage of the thing, this has a lot of overhead. This adds a lot of overhead to your thing, so it makes your program much slower, but it tends to make it equally slow at all places, so the relative measure is still okay. The absolute measure you cannot use in any way, but it gives you a relative measure and tells you how long things take. See, now it gives you these two functions where I put the profile decorator and gives you output, and you can see very detailed output line by line. You see, that's overhead the loop itself adds, and that's the time this call costs. So 99%, even if it's a fast one, but I wait 1,000th of a second in there. So this is how much it costs. And here, of course, it's 0 because this is much slower. The loop overhead is pretty much the same. You see, that's a difference. Should be the same, but yeah. Here's a little bit of difference, but it is just measurement error. If we measure it again, you will get some different numbers a little bit. So you realize this one. But you see now that this time, you can see line by line. Now you already see that where the time is. Before we just knew the function itself is slow, but now we know the exact line where the time is used up. And though you can start putting a profile in and you can see things. And this is especially useful if you call extension modules. So if you do scientific computing, you use a lot because you use a lot of extensions, and this extension calls might take a lot of time. And if you use 10 extensions call one function, then you don't know which one is which. But this line profiler is a very nice tool that helps you to analyze your code. Let's look at another example. So I have this function, there's the module called accumulate, and this is just a very simple function in there that takes an iterable, so anything that you can iterate over, and it's just and assumes you can sum things up. So there must be some kind of numbers in there, and then it sums things up, and you also get intermediate results. So what accumulate is doing. So 45 would be the sum of everything. That's the last one, but it stores all the intermediate things here, as you can see, and this is. I wrote it this way, and I actually wrote it longer than as usually you would write it, but you can see it line by line. So you have the loop here, then you get the old value, that's the last one, and then you produce a new value, and then you add the new value. You can put this everything in one line, but the purpose is you want to see how much time it takes, so I spread it on 3 lines. And if you run this through a line profiler, then you will see what happens and where's the time. So I use the same options, and I just run it through accumulate here, or over accumulate. And then you see where the time is, and you see it is pretty much equally distributed. Yeah, as you can see, the times here. The percentage is about a quarter, and a quarter for all those steps. So they have a similar time. So there's no obvious one place where you say, okay, they have to do something there and change things there. So that gives you some information. It doesn't give you a guarantee that you'll be able to optimize it, but at least you know what's going on, and you have some some information if it might be worthwhile to do something about it. So that's very nice. You have this line profiler, and you can run through. Okay, and maybe another one to give you some more information what's going on in Python, comparing different kind of calculations. So let's look at this program. To check the name myself. So that's a program, calc, I think. Calc is called. Yeah, this is a very simple function, and it's just doing a few things. It takes a number and adds 10, multiplies the number by 10, and takes the power of 10, and uses the built-in function power and the square root, and then also it makes a square root here. Instead of calling master square root itself, by setting this here, so making it a local variable instead of going to master, and just access to square root and here you can just put it here. That this thing doesn't do anything useful, but still generates bytecode instruction and takes runtime because Python has to look at the name and try to access it. And then we can run it again through our line profiler, and you see the difference. Yeah, that's very interesting. So how much time it takes to do those calculations. And you see here the plus and the multiplication takes about the same time, but the power takes much longer. So it takes much longer. And the built-in function power takes a bit longer than using the double star version. It's not much, but there's 5%, 3%, 3.5% difference here. And you can see here, if you do the square root, just accessing this name takes about the same time as just calling. So the calculation itself seems like not so expensive, so just accessing the name here. That's what its thing suggests. So that where the time goes. Yeah, so Python, everything is an object. Every time you have to ask the object and do things. And the calculation here is just built in this module. Doesn't take that long. It's just way less than a percent of calculation, and the 6% here for just looking up. And see, it's a little bit faster if I make a local variable than having this mass dot here to do things with it. So this one gives us information, and you see where you might be able to do things. Good. So we have another one here. I've forgotten the name of this file before we put the file name in there. Where I have also this similar topic about local names and not local names. And it's called, yeah. Oh, that's a different version. Sorry. Local ref. Okay, it's called local ref. Yeah. So that's a version here. You see what I'm doing now? I try to get the profile, and if I get an error, I just use a normal function. This is one way of doing it here, and I just have this. I just have to put the dummy function so they have a thing. This is just a profile. Otherwise, I write. If it exists, I take the one that the line profiler uses. Otherwise, I have my own and just return this function here. Okay, and then we have a difference between a local variable. So I do the same thing again. I have my square root as local here, and I do access this name a lot. And here I say mass.square root, and see the difference between both. And if you run it again, you see the differences. Okay, so that's one more example, and then we go local ref, it's called. Okay, and then you should see the difference, how much longer it takes to access this master square root compared with the local name. Yeah, I don't know why it takes so long to have so many loops. Yeah, oh yeah, it's a power. It's 100 million now here, so it takes a while to 10 to the power of 8. I put a big number here to see the difference. So you will see that if you do the local variable, it takes, it's probably too long. I just break it, and then you see how much time it takes here to do this, and gives you some output. I can make the number a bit smaller, so I don't have to wait so long. 1 million might be enough, and run it through and see things going on. See now, you see where the time is spent. The differences are not that big between both here; they're very close. And also, you always have to be aware that if you measure something, this line profile adds a lot of overhead, and you might measure the overhead. So that's not that really clear what you're doing. You have to really think through what you're doing. What are you measuring? Are you measuring your program, or are you measuring the tool? That might happen. That the tool takes longer than you. It's always a problem. And this maybe need some time to sit back and think through how long does it take, how much time does my tool spend on it. So things might happen. Okay, this is the first part, measuring CPU, which is very interesting to see how things go fast. But you can also measure memory. Memory, even nowadays computers have a lot of memory, it's still limited. There's still no unlimited memory, and it's always better if it's possible to don't use too much memory, because also if you lose memory, you have to allocate memory. That also eventually takes time. To work in bigger memory might take more time if you have to allocate more and put a bigger data structure and then put a smaller one. And to measure things, there are several tools to do this. And I find two tools here we are using here. And I go back to my interactive thing, and we look at profiling memory. The first tool is Hippie here, and this is located in the package Guppy. So if you download it, if you look at the web page and try to install it, you cannot take the pip install. It's the old version and works only for Python 2.6. If you want to work with Python 2.7, you have to take the trunk version. You have to go to the SVN repository and download the trunk version. Or you can even use pip, but you have to go to give it the trunk, install it from there. Or just download it from the repository and do a setup install, and then it works. So they fixed it, but there's no release yet. So it seems like the project is not really too much alive. But it still works for Python 2.7. I don't think it works with Python 3. Things are different there. But still, you can use it here. And this gives you, we look at another tool later on, Pimpler, which is doing very similar things. So two tools do very similar things. So you can import this one. I just HPI here, HPY. And then I make an instance of it, and then I can say heap, and I get the information about what's going on about the heap. And this, of course, this is running inside the notebook, so it's measuring a lot of things that are happening in my notebook. The notebook imports a lot of tools, and you can see sorted by data types what kind of data types they use. They use a lot of strings, them tuples, dictionaries, and a bunch of others. There's 581 more types of objects sitting around. Yeah. And you can see, but this one takes 49% of the memory, this 24, and all the others, here, that's a memory, I think, the percentage of the whole thing. 37, 14, and then it's getting smaller, and everything down here is less than 1% or less. So you see where the memory is located, and it gives you some interesting overview. Measure memory is not that easy, because especially in Python, because objects reference each other. So if you measure a list, what are you going to measure? Are you going to measure only the list with the pointers, or you measure the elements are inside? You're going to look at it. It's different. Of course, the elements inside are objects themselves that use memory. If I have a list of 100 integers, every integer takes memory. And if you measure the list, you can just measure the list structure itself, or all the integers that are located in. But the integers might be located in some other structures. It might be referenced somewhere else. So it's not that easy where things go. Yeah, but we see how this goes, especially if we work with lists. And then now I make a big list. You see, I make a list, with 1 billion integers here, and then I call it again. And if I do this, now all of a sudden you see, instead of the string being the first one, now integers here take up 45%, and my 1 billion integers just take up a lot of memory. So you can see this here. So you can see how many they have to count. It's 1 million and a few extra ones that are used in the program here. And then you see how much, and the list itself takes so much memory. So that's the integers in the list, and that's the list itself. Yeah, of course, the list itself has the references to these integers. Everything object, so integers have references. That's how this works. And you get some overview of what's going on with your memory. Yeah, so that's now if I delete my list again, you're back to pretty much to the state before. If you rerun this heap several times, you always get a little bit different reading. Things are very dynamic and things are changing. If you run it 10 times, you get 10 different small differences. So this is not totally exact, so you cannot do micro measurements. That's only for looking at the big picture. So you will see this is always something there. Okay, and then maybe the most important thing is you want to see the changes. You want to see what's going to change if you work with your program, what's going to change. So far we only have a big overview, global overview, what objects are there. But if you want to change, we see the changes, then you can say zref. And zref kind of sets it back to the baseline. And then, if you allocate some objects, then you will see the changes, and you can see how big this object you just did is, approximately. So it's not exact, but it's pretty good. That's what I'm doing here. I set ref, and if I do this, then I get this reading here. So instead of 584 more objects, I get only 4 more objects. There's way fewer. There are still something left, but this is pretty much 0. Yeah, see, if you look at the total size, it's that big. Yeah, this is 21 million bytes, says here. And now we're down to 9,000 bytes. That's pretty much 0. So you don't really get 0. So if you run this again, you might get a little bit different reading. So that's your 0. Now I can allocate my list again, create my list here, and do this again, and then I see the changes. This is pretty much 0, and the list is so big, then you see, okay, now 75% is taken up here, taken up by the integers, and 25% is taken up by the list. And the others is just very small. The numbers are much smaller. Then you see how the memory is going. So you can always go with zref, set it back, and then create your object and see how much memory your object needs to be created. And you get some overview. That's very interesting to do, to see what's going on. Yeah. Now, if you do this several times, you see, I do this zref again, and I do this several times. I get a bit different readings, some different numbers. They are small compared to what you're going to want to measure. So if you want to measure big memory usage, and they are pretty small, and they are kind of close to 0 with very similar numbers. So you can do it many times. You get the same thing. This object has quite a few information, and I want to show you a few. So if you make the instance of this heap here, then you can access it, and you can do something like this. You can just index it like as it would be a list, and with index 0 you get the first line. So you can do this, and then you get the first line. So this allows you to programmatically go through the results and just sort out. You can go, it's a list, and you can look inside and do something with it and work with it and write your own tools to put in. Because those memory things, usually they don't really help if you put them in tests. You want to put them somewhere in the real system, see what's going on. Because in the test, you might not be able to reproduce the memory error. If you can, it's fine, but very often you cannot. Then you might need to put it in for a while to see what's going on, and then you can go programmatically through this results and generate the numbers, and in the end generate some statistics. It will be very different depending on your application. First, you can make some global. You see have some big impression where things going on. Then you can look inside this objects and with zref set things back and see the changes. So then you can have a bunch of information. I just have a few examples here. Like you can have byte type. So everything what I'm showing here is written in the handout. So you see it's quite a bit. So you can read it, and also this thing of course they have pretty good documentation. So you can have more things in here. So you can sort it by byte type. For instance, here by type, and you see this sorted by type, and you can sort it by other criteria. And with more, so underscore gives you the last output. So you see 14 more, then you get more information. So underscore more, that's the normal Python for the last output. In IPython you could say underscore 36, you get a 36 here also. So I get more information about this one. And I can also sort it here by referrers who's referring this, and you can see sorted by referrers. So there's all kind of information in there, what's going on, who is using memory, and what's going on in your memory. Okay, I wrote a small tool, actually, that's helping you to do this. Let's look at this tool, and I use a decorator again. So decorators are very nice tools to write to help you to measure things. Okay. We go into the file memory size. So we have different versions for memory to measure the memory, and I use a version with the CP, and I have a version with the Pimpler that helps you to measure the memory. Let's look inside gedit memory size. So memory size HP. So okay, so now who's familiar with decorators? Who wrote a decorator himself or herself? A few people. Thank you. The decorator is it's just this @ sign is just syntactic shortcut. You could have written decorators with all the earlier versions with Python, because everything in Python is an object, and decorator is just a function that takes a function and returns a new function. That's usually what you're doing. So you take a function and add something to the function at runtime, but rather instead of writing the source code into the function, you can write it once and then with a small decorator syntax use it all over the place. That's the whole thing. So you can always achieve it by copy-paste source code around, which is not a good idea. If you copy something 100 times and you want to change it, you have to change 100 places. And with a decorator, you have a very nice way to do this. And that's what I'm doing here. I would like to measure something. And measuring is one of those applications of a decorator. And so I write a decorator, and this takes my original function I would like to measure here. And then I use funcToolWraps. funcToolWraps is a helper. It's itself a decorator, but it helps you because it keeps the docstring and everything, the function name in place. If you don't do this, you lose your function name in your docstring, because the wrapping function would replace it. But this funcToolWraps is doing the right thing. You don't have to worry about it. And then you use this magic stuff here with args and star args and W star keyword args, which is very common. So this one's packing all the position arguments, and this one all the keyword arguments into a tuple and to a dictionary. And this is, we just do this here, so we can take these arguments to hand over to the original function. So you might have seen this one. That's a very powerful technique. So this allows you to write a wrapper for any kind of function, no matter if it takes no argument at all, or takes all positional or keyword or any mixture out of it. That's what it's doing. And then I do this additional thing. I just say, okay, I make an instance of this HPY here, and then I do the setref we just did, and then I measure the memory, the initial memory, and then I call my function, and I return my function result, and I do try finally. So that's what try finally is good for, because if I do this, I will always get to the finally. Even though the return is here, I always will execute the finally. That's what finally guarantees. So it will do the finally before the returns. So even though it looks a bit different. So that's what I'm doing. I try to call the function and return the result. And then I just use memory. Memory is just dictionary here. So you might use a different kind of thing. I just use a global dictionary. And in this dictionary, I put the function name. You see, function has an underscore name. And this is very useful because I don't have to put the function name by hand in. It just takes a function name. Every function knows its name. It's defined. You can change it. Actually, that's what funcToolWraps is doing, is changing the name. So you have the original function name. And then you just measure, you put the result. And you measure the memory usage now and subtract the one before. And then you know pretty much, roughly, how much memory this function call used. If you have a function without side effects, it should be 0 or close to 0. They hadn't changed anything. If this thing has changed some global variable and appended a million elements to a list, you would see a difference. So then you can see this function, does it impact my memory? And if I do it a lot, then you will see if I have a memory leak, this function could be the one that's causing a memory leak. And the only thing you have to put this decorator on. So this is very flexible because you build the tool yourself. It's not too complicated, and you can adapt it the way whatever you want. So instead of writing a dictionary, you can write a thing to a database or to a file or something, and you can keep it running for a long time, and you have some log over weeks if you have something. Those memory things are problems often are for a program to run long. Then even a small memory problem can accumulate over time. It never cleans it. And this object's getting more and more. Eventually, the memory will be used up if it runs long enough. Yeah, that is one of the applications. So. And then for this, you can see which one is using memory, and then you of course write a few tools to do this. So this you always have to do a little bit tooling because the standard tools they might fit, but very often you have to adapt them. And this is a very flexible approach. You can do this. So if you do this now here, that's how to use it. I just use my decorator, and that's it. You see, and here I say return number. So I return this a new thing, and then you will see if this how much memory you used for this, because you measure the memory before and after the function. Then if you return this number and you make big number here, and then I call this function and see. So let's have a look how this looks like. So if I call Python, so everything's Python 2.7 by the way here, and memory size age. Yeah, so this one should go off now and should do it. See, and now it gives you an amount of memory in bytes here, and this could be a much bigger dictionary. And of course, the problem is if you call this function again, as a dictionary will override it. So if you want to keep more calls, you have to change this somehow. You don't put it in one dictionary, then you have to say we have it already. We just put a list and append it or something like this. So you can adapt it to whatever you want. Or you want to have the biggest one. So you just run a maximum. You take the original number, and the one that comes and takes the bigger one and store it there. Eventually, you have the maximum. Depends what you're interested in. So that's you can adapt it to the way you want. It's not that difficult. You can look inside, and maybe you have to read about decorators a little bit. But even if you don't understand decorators in detail, there's just a recipe you can use. And the only thing you need to change, you have to go inside here and change what's doing here. So the scaffolding for this decorator is here, but if you want to do something else, so instead of writing in a dictionary, you just append it and you have a list of all the memory usages over time. And you can also save a timestamp and whatever you want. So that's not that difficult, and you can use the same scaffolding. So that's one of the memories. And I have a different version here, which is memory grows. It's called. And also a version here. This one is different. Here I have a different approach. This one I don't use a decorator. Decorators are nice. The disadvantage, you have to go into the code and put a decorator all over the place you want to measure. In Python you can even use other techniques, and here I use a technique, I just hand in the function explicitly. So you could theoretically go over modules and figure out the function automatically and put them in a measure automatically, if you know the signature of the function. So, but this is a different approach that can be useful also, and it's doing very similar things. You see, I hand in the function and have this double star and double star thing here, star and double star. And now I do, this is very similar. I make an instance, set the memory back to 0, measures initial memory, call the function, then I return the, this way I don't even return the function result. I'm not interested in the function result, I'm only interested in the used memory here. And then I do the same thing, but the usage is different. So here in this case, I don't put a decorator in front of the function, which I did last time. But rather, I have these two functions. I have a big number which returns a number, yeah. And then I have another one which is changing a list. You see, I have data, a global list, and in this function, I append something to the list. So I have a different effect. And then I can use my check memory and just as a first argument put the function I would like to measure, and the second one the argument. That's how this works. Yeah, this is a function, and that's arguments here. So I can put the arguments. Yeah, and this star double star takes care of doing the right things with the arguments for me. You don't have to worry about it. And then I just print it. So like if you have 150 functions that are similar, all takes the same kind of arguments, then you could automate it. You don't have to put 150 decorators in there. You can automate it if you have this case. Let's just go to the module, figure out which one is a callable, and just throw them all in there and measure it. So automating is very important, because you want to reproduce things, you want to change things, and if you spend 2 hours to putting something in, or change something, you spend another 2 hours, you're not going to do it often. If you automate it, you spend 2 hours to automate it, and then you can change it 50 times. That gives you a lot of information. So you want to automate things. And this is something you can do, and if you run it, you see the difference. So we have this memory growth instead of size. So the HP Y version here, and you see the first one just returns this list. If you look at the source code, yeah, this first function just returns the list, and we call this function here without doing anything. We don't keep a reference on the result. We just throw away the result. In this case, that's how we set it up. It's not really useful, but for demonstration purposes. Here we also throw the result, but this one is changing this data structure, this built-in, and then you see this growing. Yeah, you see this growing because I changed this data structure, and that's something that you want to know. If somebody globals can be difficult. So somebody's changing a global data structure and it's growing, and you don't see it, you never free this for some reason. Yeah, so there's probably something wrong how the program is structured, but at least you figure this out and you see it and you can fix it maybe. Yeah, so that's just an example. Boiled down to the smallest thing that can cause this problem. Okay, this is a HEPI. There's another version, of course. The HEPI is just, yeah, now it used to be only 2.6. Now at least it's 2.7. There's a similar one which I can go over quickly. Pimpler is doing very similar things. So if you go to Pimpler, it's doing very similar things. This project came out of 3 other projects that merged together, and I think it's pure Python, whereas HEPI has some C inside. And this is doing very similar things. Has a little bit different syntax here and there, but you get the same. So I haven't tested it in Python 3. I'm not sure if it works, but Python 2 it works. And see, now I can do very similar things. I import it and make an instance of the summary tracker, and then I see something. It looks very similar. So you have the total size, you have the objects, how many objects are here, and you get the data types, a list and string and so on. Yeah, and then you have a diff. So you don't have to do setting to 0 yourself. This one has a convenience function called diff, which is doing exactly the same thing. And then you do the diff then before here, and that's 0. If you do this diffing, and then you can setting the 0. I have to say, yeah, that's the same thing as the same thing as we did with the set ref. This is called print diff here, and then we allocate a list and do this again, and then you see the differences. So now I wrote the same tools very much. So just a very quick look. So very similar tools. Just instead of using HEPI, we use this Pimpler. Let's have a look how this thing looks like. So I use the same approach. Memory, size, Pimpler. Yeah, so it's very similar. Yeah, so you can use all the same techniques. I have the imported, of course. I use func tools. I have my global dictionary where I store stuff, and I write my decorator, which takes a function, and then I use my func tool reps. So that's the same recipe. So even if I don't understand the details, you can take it as a recipe that works. And then I define this function that's going to replace my original function. And here now, instead of doing this, I do the summary checker. And the problem is this diff is not really going to 0. So I call it 5 times in a row to get as close to as possible to 0. Of course, this adds overhead a little bit. Might add quite a bit of overhead, but in this time we are not interested in CPU usage. So you don't want to mix CPU measurement and this measurement, because then you would measure probably this diff takes much more CPU than your function. So you have to be careful. If you want to measure pose, you have to really think what you're doing. So otherwise, you measure the measurement and you get very screwed results. So it can be difficult. So now again, we call the function to this. It looks very similar, and we store our things and just have this few lines replaced, but the mechanical things are the same. And then if you call this, then you should get some very similar. So this one, and just instead of opening, I call this Python, and you see, you should get similar results than The other one is just a different version, and you can do the same thing. I don't know, maybe I put a big number on there that takes so long. 1 million. Yeah, those tools, they take quite a while, because they have to go and ask all the objects and look at the sizes, you see. And this one gives you, had a little bit different output, so, and also it keeps also the list, how much, you have one list with this size, so you have integers, so you have about, you see it's interesting, you don't have 1 million integers, you have only 999, because Python is reusing this something, yeah, here. And though the objects they have been there before, they don't count. They're not recreated, because in Python 2, the numbers between -5 and 256 are reused. Yeah, and they've been there. They just put a new reference. They don't create newer numbers, so there are a few missing here. You see, it's about 139 numbers missing in here. So you have to be careful what's going on. If you use a different implementation, these limits are different. If you use Iron Python, this limit you will get different numbers between -1,000 and 1,000 used to be. I'm not sure the current version, but used to be reused, just with references. So you get some information what's going on, and this Pimpler here has a little bit, I kept it this way, so it has a little more detailed information at this place. You could get it out of this, if you also by taking apart the output, but this one gives you a list right away, like this. And if you look at this memory growth thing, this is exactly the same, again, so just quickly, memory growth, Pimpler. So if you look inside, so we use exactly the same technology, and we only replace this bit here. This bit where we use a measure thing. So, and if you find a different library that's doing similar measurements, but it's better, because it's faster or something, you could use the same scaffolding and just put a different library in. If they kind of set it to 0 and do something and measure, that's usually how you do it, then you would get the same result. By the way, all those comments here, so if you look at the handout, I use these comments here to refer to the lines. So if you read through, in parentheses, usually I use those things, and you will find your way through the things. So those things should be kind of self-contained. If you read through, you should be able to understand what's going on in here. Good. Then I did some interesting comparison about lists. Lists, it's a very important data structure in Python, and I did some tooling and applied some of those tools to lists, and I have written this list allocation steps, or list growth. That's a function here I wrote to see how the a list is growing. You see, I have this Pimpler has a size of, and the size of gives me the memory usage. Yeah, and they have two different versions, size of and flat size. So one of them is measuring only the list as it is and doesn't measure the integers contained in the list. The other one measures the list including all the elements and the references. So that's a different thing. So if you go to Python sys module, has a get size of, which is very similar. So you can say get size of list, and it gives you the size of a list, but it doesn't give you the size of all the elements that are contained. So it is not recursive. It doesn't go inside. So that's what is was doing here. And now I'm using this one. See, I have generate a list. Yeah, and here I use this size function, and I have two different size functions. So I write this function only once, and I either use flat size or size of and put it in here as a function. Here the function as an argument, and use this function to generate to calculate the memory. So I do this here, and I have this memory of the list, and then I go through and append an element to my list, and append the size of this list to my memory function. So every time I append something to my list, I measure the memory size again. And then I use matplotlib. So that's just some helper code, so that's why I put it down here. I just have some helper code here to plot this result. So let's look at the result when we do this. So I have Python, it's called memory size, no, pimpler list. So if we execute it, takes a while to, but this graph gives you some. So now matplotlib starts in the background and produces this graph, and it looks like this. You see, that's what happens with the list. When you see, I append one element at a time up to 1,000 here or something. No, that's the allocations. The elements is here. 10,000 elements. Yeah, and every time I reach a certain limit, Python increases the size of the list. So it doesn't increase the size of the list every time I append. It usually kind of doubles the size of the list as soon as I reach a certain limit, or puts it like 50% more, something like this. So you have always some over allocation of the list. So the append is very inexpensive. So you need very few allocations to increase the list. So append is a very inexpensive operation compared to insert in Python, where you change the whole list. Every time you do insert, you have to reallocate the whole list because you put it somewhere in the list. If you do append, you have to allocate already, just put it in. So it's very fast, and then you reach a limit, and you get a bigger chunk again. And that's what this thing is doing. You see this is a bigger chunk. Every time you get a bigger chunk, getting bigger and bigger. And this is one allocation, and then you don't need to allocate anymore. You're happy, and then you can just append, and you reach it, then you allocate again. That's what this graph is doing here. And it's just produced with this very script I showed you there, and it can be pretty interesting. So, and I produce another one, and this one is measuring the list plus the integers. So this is the other function, not the flat size, but the size of. And see, though you don't use this pronounced steps, you still see this increase where the list is gets bigger, but now you see continuously because you're allocating integers here all the time. That's this continuous increase of the integers, and then the list gets bigger again, and those big steps are kind of smoothed out because we have this integers growing at the same time. So that's a different function. You see, either you want only the object itself, or you want also other objects that are referenced by there. That's something you can do. But I think that's a very interesting insight. You can see what's going on and how Python is working. That might be helpful. So the source code, so we don't have time to go into matplotlib here, just put it in there. So if you know matplotlib, it's fine, otherwise you need to read, but the thing works and it gives you some plots. So you could use some other plotting tool, but matplotlib is very convenient, and just a few lines you get a pretty decent plot. So that's another function here, that's a built-in size of. So if you go into the source code, you will see this. I put in the flat size, I put in a size. The flat size is the first step one. A size of is the one with the smooth one. And this get size of is the same one as flat size, obviously, for this case. I'm not sure if it's for all cases, but for this case it is. So Python has this get size of function in the standard module. So I wouldn't need this special install pimpler to produce this graph for this case. But it's not recursive, so you don't get the smoothed out version here. Okay, this is a measurement of with pimpler, and you can produce all these plots. And I have another version which is similar, a little bit of variation on it. Let's have a look at it. I have to close this one. It doesn't let me. So that's very similar. List allocation steps. And actually that's a similar thing. This was takes get size of as a default, and it's just producing this is the integer size of an integer here, and I make an instance of an integer and use my size function, either get size of or other function to get the size of an integer. And this is the old size of my list, and do the same thing again. I go through the length of my list, append to my list, and I get the new size here of my list, and then I just say if this new size minus the old size is greater than the in size, I increment my step here. and return the steps. So then this one measures just how many steps you need to allocate the list. So very similar to the other one, but really measured here and counted there. Then you see every time this is bigger, then you made this list bigger. And then I have a few examples and run it for different numbers between 10 and 10 million here. So you see how things work, and you see the allocation steps. So it looks very similar, but it's a little different approach. So if I run this one, Python list allocation steps, then you see now it's producing this. If I have, even if I have 10 million elements, it's still running. I only have like 100 or so allocation steps in Python. That's very important. It's still doing the allocation. It's 104. And using this flat size, at least the steps agree. So that's the same thing. That of course, and then, yeah. So that's the number of steps, and then you can also make a matplotlib, which I haven't done here. But you see, if you start from an empty list and go to 10, you have 3 allocation steps, and then you're getting smaller and smaller and smaller. And if you go to 10 million here, you only have 104 allocation steps. That's something you can get out with those tools. Okay, good. That was an overview about measuring CPU, measuring memory usage, very important things. Those tools are bigger. There are some more things you can do, but I think it should be good enough to get you an overview. And you can see how you can use some Python decorator, which is a little bit meta programming, as you can see, tools to get some very low effort methods to get into your code and see what's happening. So, of course, if you always have to go in and copy paste a lot of code and put a lot of things in the measure, you're not going to do it. But if it's just a decorator there, that you might do it. It's much easier. Okay, this concludes the first 2 sections. Are there any questions about this measurement of CPU and memory things? Yeah? Yeah, so it depends. Yeah, this is measuring CPU seconds. Yeah, this one just gives you this. If I use time it, and this gives you a timestamp. It gives you a timestamp. It gives you the time it really takes. There's a real time it takes. Yeah, so that's what we're doing here. So if I run it and run something else, it takes longer because something else might get into the way. The prof.
Not clock time, not CPU time.
Yes, I think there must be something in there. So I'm not really sure. I have to be honest, but I think there are some ways, because if you use a normal time command, you also have this different kind of things, and that's in there. So if you have some I/O going on that's blocking, and it's just changing results, there is something there. So I have to look inside. There's one. Yeah.
The profile is very useful to see where the time is being sucked up, but sometimes I care about real time, clock time versus CPU time.
Yeah. So it's a good question. So I have to do research myself exactly how it works. So those things which is measured there. So I cannot. Maybe in the break I can answer the question. Yeah.
Can you recommend a process for measuring like Python gaming or something like that, and that's run non-interactively, like a long-term? Can you use syslog or something? How do you?
Yeah. So he asked about measuring some long-time running things. That's difficult. If you run something under the profiler, you cannot run those things under the profile if you want to use CPU. If the memory I showed you, you can use the thing, but also this also might increase your runtime a lot if you measure the memory all the time. You might spend way more time measuring the memory than what you're actually doing. Yeah, depends. Yeah. So that's difficult. So this the first modules I showed you. This timer thing could be something. Are we the very first? No. One of the very first ones, I just close a few of here. This one is you could also use a decorator approach. Very similar what I use for the memory. You could use the same approach for the CPU and use decorators yourself. And run it with and without a decorator to see the difference. But if you cannot run it, like especially if you use line profiler, it increases the runtimes maybe orders of magnitude compared to what you do before. So that's not the way to put it in production systems. And profile me, so Pystone converter. No, actually I have it in a later section. In a later section I have one where you just use the timeit module yourself. So if you use a timeit module, let's go to the interactive. So I go to my interactive thing here. So you can say import timeit. You should always, if you measure time, you should always use timeit. Yeah, so if you use this one, because there are some differences between Windows and POSIX systems, time measurement. If on the POSIX you can always use time. If you do it on Windows, it's pretty coarse. So on the Windows you recommend to use time clock, but time clock has a different meaning on the POSIX. So, but timeit helps you on this because you say default timer, and this default timer gives you a timestamp. Yeah. And if you have to call it again, you get another timestamp. See, if I just copy this one, and all the time it took me to do this, I get another timestamp here. And if I subtract those times, so if I say this is start, that would be my first timestamp. And then I say timeit minus start, then it gives me the time it took me to type those things. Now it takes 9.5 seconds. So that's a time. And this one you could use this decorator approach and put it in a decorator, same as we did the memory, and measure the time. So this is something you could run, but of course this might also cause overhead. It causes overhead, just a question how much compared to what you're doing. But you can always have this dummy profile decorator, so to speak, which is doing nothing, just returns the original function, and then you can turn it off and on just by changing this one thing. And then you can see how much overhead it has compared if it makes sense to do it. Yeah, then you could log things. You could log in and do things. Yeah?
Yeah, you mentioned that PD and Müller serve a very similar function. Can you give your opinion on which package is better, or which one, if you had only one,
the question was about Hippie and Pimpler. It's a tough one. I started out with Hippie, and then Hippie fell behind. It was only Python 2.6, and I started with Pimpler. So they are very similar, and if you just do basic things, the overhead to learn is not big. You can try both to see if there are differences. One can do this better, one could do that better. I don't have a strong preference on either one. So the question was which one is better. Yeah. So I don't have a preference. I don't have a recommendation which one. Depends very much on the use. You have to go much more in detail and do something. And they all the tools have some small problems here and there. I'm sure it's always like this. If you do something real thing, there's something, and then you have to do some bigger projects. This is just more demonstration. It depends what you're doing. You might have one. I can give you say this is better. So the Pimpler seems more active in terms of development. The CP is kind of. So the last release was 2009. So they're still developing, but it does no release. So that says something. Yeah.
Will there be Python 3 versions of these?
Pimpler, I'm not sure. I think Pimpler's pure Python and it should work. So because they use this get size of, which is also exists in Python 3. Though if it's pure Python, it's much easier to do it if you're going down to the C. So there might be. So I'm not involved in the development of those projects. I'm just using it, and I don't know too much about what people are doing with it. So. Good. I would suggest we do break now because we just cut in the topics. We want to go to different topic algorithms. So we are 5 minutes early with the break, so we should also start a bit earlier. So keep in time. Of course, we have quite a bit to cover, but it would make sense to start with 5 minutes and break in the middle somewhere. So let's meet here again, no later than 45. 45 should be 20 minutes break. There should be something to drink and some breakfast outside, if I'm right. Again, I want to repeat some things. If you haven't signed in, please sign in and take a handout. And if you want some instructions about installing things, I can put up the links if you came late. Or something might have come late, just you can fix this in the breaks if you want to work along if you feel like. Otherwise, we meet here again 45 and continue with algorithms.
La la. Yep. Yeah, it's fine sound, I would say.
Can you hear anything? No. Yeah. Is it right? So yeah. So this is my normal voice. I always speak when I speak normally. I can speak louder if it's necessary. There's no problem. If you want, if you want me to. Yeah, my trip here. So I arrived. Actually, I arrived the day before yesterday. Because I always put a buffer day in just in case anything goes wrong with the airplane. I have bad experience. But the airplane is delayed. I had one conference. I was 24 hours late. I always have one day early, just to make sure I'm here when it starts. Is it good like this? Keep going. So I have to tell my life story. No. Okay, that's still loud, I guess. So I'm just touching up here the last things I'm doing here, just to make it a bit more interactive. I just have them last touch-ups here. I can turn it off. Okay, I turn it off.
Yeah. Yeah, that's working.
It's on. It says on. Group 10, channel 1. I'm on here with this machine. So I just put it to my belt. Left side probably. Hope so it wouldn't break the clip here. Okay. So, and I just can turn it off with this button, I guess. Do you want me to keep talking? Yeah. Okay, then I keep talking about it a bit. A few things. Very nice. The handouts are here, because my very first tutorial I carried them from Germany, and my luggage didn't arrive for 3 days, so I had to teach the tutorial without the handouts, which I based my whole thing on, so which is not very nice. So I can walk around here, yeah. If there are any problem with feedback, if I walk if I want in front of people, that I get feedback, so to get some strange noise. So if I want in front of the speakers, do I get problems? Like if I walk around? So do not. So I should stay in the front.
Yeah, as long as you're in this area, not in front of the speakers, you're fine.
Yeah, okay, because I know that. Okay, good. So yeah, turn it off. Let's continue. 20 minutes is short, so long wait in the breakfast. Long queue. Let's continue with some different topics. So we have this measuring, which is very important. The next one is some algorithmic things. A few things in general about algorithms and Python special, how to do things, and a few things you should avoid working with Python. So the first one is this very beloved string concatenation. That's something you always do. You want to add together strings, and there are different ways of doing things. And since we know Python strings are immutable, that has some implications. And let's have a look at it. So actually, it's supposed to be an exercise, but I have a solution to the exercise. I concatenate strings in different ways. So in Python, you can concatenate the strings either keeping a string, or first you can go to a list and work with a list. So this concatenate. So I think I have given you as a download because it's supposed to be an exercise, but it's not that difficult. Concatenation. So this is a version that works with Python 2 and Python 3. That's why there's a little bit fiddling up there to make it work. And the thing is, actually, the real code is here. You start with an empty string, and you want to concatenate a string. One thing is to use a plus equal sign and stay with a string. So I start with a string, have a loop over n, and then I just say empty string plus equals a. And next time it's AA, next time it's AA, and so on. It's just a complete very silly thing, but that's the thing. And I just do this time, default time, I just show the measure the time. So like this one, I measure the time by hand, I don't put a profile or anything like this. It's not even a function every module. And then I do the same thing, but I don't use a string, I use a list. You see, I use a list. And then I just do append. We just learned append is a cheap thing. Python's doing very few allocations, you saw the graph. That's what I'm applying here. I do so the graph, and then I just append, and I end up with a list of all A's. So of course, you could always generate this one in one instruction. It would be easy, but just to see this, like, let's say that A is something different every time it comes from somewhere. Let's just append it. Then at the end, still have a list. I just use join to generate a string. So that's a common case in Python. Use an empty string join and put a list in, and then I get this one. So if I do this and I run this, then I just have this measuring. The rest is just time measuring thing. And now if you run this as different versions of Python, you'll see some interesting results. So I'm here, and I just run this Python 2.7. Maybe I go a little bit lower. What number do I use here? 7, you don't need so big. 100,000 should be fine for our purposes. If I do this, then you see it takes about the same amount of time. If you had used a very old version of Python, that would be a very different result. If you use Python 3, that's Python 3.3 here, what I'm using, regular version, then you see there's a difference. So the plus time, it's about twice as long as the append time, which is a list second version. Interesting is if you use PyPy. We're going to look at PyPy very quickly. PyPy is a very interesting project. Just turned 10 years. 10 years ago they started with a research project implementing Python and Python. My little logo, the snake that bites its own tail, this is of course is Python in Python. Very interesting project. They have a very good just-in-time compiler. They can make Python very fast. So, but if I run this program with PyPy, then you will see a very interesting result. You see now you don't have about the same size, they have a factor of 36 difference. So this plus equal is much slower than the append. Because strings in Python are immutable. And every time you do the plus equal, you have to create a new string. In C Python, there are some optimization going on in Python itself. In PyPy, it's not. If you want to, actually, I researched it, there's a trick you can. If you compile PyPy with this flag here, then it's supposed to go faster. I haven't tried. So compiling PyPy is not the easiest thing to do, so I haven't tried. But See, if you use JSON, which is also doesn't do this optimization, you would have similar similar results. So happen with IAM Python, and we need a sort of window to do this. Oh yeah, this JSON is 2.5. It doesn't have the from future import, which is nice. So you have to command out from future import here. Because to make it run with Python 3, just to put a little bit in. So now with JSON, you will also see a difference. So this is something. That's why this plus we should, even though in C Python is pretty much the same time usage, we see now the ratio is 21. The extra parentheses is just I have this for the print function, then make a tuple out of it. Don't worry about this one. So this plus equal you should use, even though in C Python you won't see a difference, but if you might change to different implementation Python, who knows, and then that's an anti-pattern. And in all the versions of Python you should need something like this. And this is the reason is we saw every time you do this, you would need to allocate it to a string. So they use otherwise they use a buffer, they do some tricks behind, but if you don't, you would have every time you have 100,000 new allocations. Compared to this, if you look at this here, 100 is only 65 here for the list. That's a difference, and this costs time. Yeah, those kind of things you should think about it when you do it. Then this is one of those anti-patterns. Let's look at some other smaller things you can do. So this is string concatenation as one of them. The other ones are lists, and there should be lists here. So you can this is just a markdown here, there's no problem. So run it again. List and generator comprehension. So if you work with Python 3 a little bit, you will realize there's a lot of iterators and generators all over the place. In old versions you have lists. Like you say dictionary.keys, you usually get a list. With Python 2, with Python 3 you get a view, which is something similar to an iterator. So it's something that doesn't generate this key list in memory, but gives you something you can iterate over, pretty much. Yeah. So, and this is something this will generate. So they don't generate this in memory, but these comprehensions are a bit faster if you use list comprehensions, something like this in Python. So you have these two options. Then if you do a list comprehension, then you might be a little bit faster. So this is not too bad a deal, because instead of 3 lines, you only use 1, and you are a little bit faster. So that's an optimization you can do, so you don't add a lot of things, and even though it's the same, you don't lose anything. So usually list conventions are a little bit faster. But the real optimization is like this. Now we use a generator here. You see, I don't use this curly brackets here. I don't produce the intermediate list because I don't need it. I just need the sum. So I don't need to allocate this big list, potentially big list, and then go over it. I just have a generator which gives me one element at a time, and this is enough for the sum. And I can even drop the extra parentheses here because it's unique in Python, you don't have to do this. And this can be something you save in memory, but you also save the time to allocate this list, which is also something, if you do it often, that might be something important for you. But this is something, use the new features. Most of the time, your best bet is to put the burden on Python itself, use the generators, and Python's doing the right thing. That's most of the time a good optimization. It's Pythonic, you use it built-in Pythons, and most of the time they are faster. Unless you want to like demonstrate an algorithm or something like this, you should use the built-in things. So there's some small things that make it faster. So don't use this plus equals for string concatenation, and use the built-in lists and generators here. And actually you have the thing in the exercise here, so we skip it here. So use different types of things like range and x-range, which is something similar with range, always generates a full list. X-range gives you an x-range object which you can iterate over if you like to, without creating the list. And this means you can make very big x-range objects which you cannot with range, because that will be with Python 2. There will be some limit in the memory, and you won't be able to create this list in the first place. So let's look at data structures. So algorithms and data structures are very closely related. Data structures, no, not yet. Okay, I still have some algorithmic things. So if you look at the handout, so it's also a little bit fast, about the global and local. So let's have a look at this file. It's global and local. We touched upon this. You remember this square root, the math square root thing? And I have it a little bit different. Local global. So I have a local global here. See, I use a global. So if you use globals in Python, you should use all capital letters. That's like more constants in global. And I have this global one. And in this loop here, in the X-range loop, I access the global one. And here, I set the global one as a local as the first thing, and then I just access the local one here. It's the same thing, just a different name for the same thing. They're doing exactly the same, but this one line has some impact. And now I just have this use C profile and run C profile. So I use some of the tools. So I tend to vary the tools we're using now. I use C profile as we did before, and run the profile and print out the stats and do this 100 million times here and see what's coming out of it. If you see a difference doing those things, going to local and global. So if we're running Python on it, then it might take a while, a few seconds. Yeah, so I do with it. And you see the time. Let's look at the source code, which one is which here. So we have this function, repeat and a repeat local, they're called. Repeat is the global one. And this is a repeat and repeat local. So the difference are not very big. Here it says 5, it says 4. So about 10% or something. So it's not a lot, but it's measurable in this case. I have a second version which is going even one step deeper. So not only the local, but the built-in. Built-in. And I'm doing the following here. Here I access the built-in true. So in Python 2, true is a built-in. So Python, every time I access true, Python has to go look in the local namespace, cannot find true, goes to the local global namespace here, cannot find true, and goes to the built-in. That's every time we do. Here I just said make the true a local one. I call it lowercase true, just as an example. If I run this one, then I should see some difference between two. So there are some impact. So you should see the difference. And it will be a bit bigger because we have one extra lookup. You see, if I run this repeat, I'm here with 6, and here I have 4. So it's a bit different. So it's not a lot. It's not like orders of magnitude you can gain. But if you do this a lot, and have a lot of inner loops, then this might be something that's just worthwhile to do. Okay, this is just this local global thing. Let's go and switch to the right data structure. So algorithms and data structures are connected. The algorithms all have big data structures with them in Python, and you can get quite a few things out of them. Maybe the very interesting thing is if you have a list and a set. So you can do different things with lists and sets. That's a very simple thing. So you want to search something here. So I use this very simple timing approach here. So the time measuring is included in this code here just for demonstration purposes. And this is very easy. I just make a list of this size, and then I just check if some element is in my list. And n is the last one. It's not even there. So it has to go to the whole list. Yeah, because range goes from 0 to n minus 1, and if you look for n, has to go to the whole list. So I'm not really interested in the result. I'm rather interested in going through the whole thing, and then I measure the time. And then I do the same thing, but instead of generating a list, I generate a set. So, and that's a very different kind of thing. And then if you run this, then I just run a comparing and I just measure the time. The problem is the search time of the set sometimes returns a 0 here. I had this the first time. It's so fast that it gives me 0, and if you divide by 0, that's not very healthy. So I say, okay, I set at the minimum of power -7 here, 10 to the -7, to get some result. It's just because, I don't know, sometimes it's 0, and then if you want to create a ratio, then it bombs. Because that's what I'm doing. I measure this time, I measure this time, there's two functions here, and then it generates a ratio. And if I run this one, so I just ran it here, it is just a loop, and do it from 10 to 10 million. So it's 10 to the power of 1, 10, and 10 to the power of 7 is 10 million. Call it E here, the raised here. And then you see the time here it takes to do this, and you see if you look at the times exactly, then the search time for the set doesn't depend on the size. It's pretty much the same no matter how big the set is, whereas for the list it increases pretty much linearly. That's a very, very big difference. So if it's small, it doesn't matter too much, the factor of 2. But you see it's increasing very quickly, and if you have this 10 million, yeah, here, then you see it's a factor of close to 5,000, and that's a lot. That's 4 orders of magnitude, 1 order of magnitude difference you get only by using a set. You don't have to do a lot, you just have to convert to a set. Or every time you search with something, then sets are your friend instead of using a list. But of course, this is only half the truth, so that's pretty obvious. But if you convert an existing list, because you have a list anyway into a set, this also costs time. So if you search only once, converting a list to a set might not be very useful. They have another function. There I also not only measure this lookup time as I did here. You see this it's important. The start is just in front of the lookup. Here is the start is in front of where I create a set. So I have a list, and out of this list I create a set, and I measure this time also. And this means I have to move the whole list into a set, and then it takes also time. So if you look only once, then with the same comparison now, then you see you won't gain anything, you lose something, because we have to go through the whole list and make a set out of it, which costs more time than searching the list once. So this thing is set is always faster than a list. It's true in general, but if you only look only once, it doesn't make sense to do this, because you have to generate the set first, so it takes more time than looking up the list in the first place. But of course, if you need to look up multiple times, and I change my function a little bit, instead of only looking up once, I have a factor m, which I look up not only once, but twice, or 10 times, or even more. And then if I write this function like this, so I have another loop in here, which is doing the lookup several times, then you see you get more worthwhile the more often you do this, because you need a conversion only once, and then you are through, and then you gain something because the lookup is much faster. There, it's the same version for the set. I do several lookups here, but for the you just see that they're just yeah, this is set, that's the right way. So the list is the set, and I generate the set from this. And then compare them to the same thing and give them the same n and m, both of them, and I run through. So I run through again between 10 and 10 billion, and now I run through, we have used it for 1, 10, and 100 repetitions. There's a repeat here, and if I do this, you get a result like this. You see, for the small ones, it doesn't matter too much, yeah? So if you have even 100 repetitions, you can get only a factor of 2. But the bigger you get, you see the big ones for this 10 million, then you're 40 times faster. So if you look up several times, then or search for something that makes sense to convert it to a set. If it's only once, then it doesn't really matter too much. Yeah, this is something you need to always put it in the context. So those general rules are good, but you always need to put it in the context and see, does it really work for my use case? My use case might be a little bit different, and there might be something that just is opposite to what I want to achieve, and if you have to convert it to a set, then that's something. So keep in mind. Okay, the next one, this is a lists versus sets for this lookup. So sets are very powerful, and you can do more things with sets. So let's say we have a string A, B, C, D, and so on. And I convert it to a list here. I have a list A and a list B, and I would like to check which ones are on both. So the naive approach would be you say, okay, I have this is in both. I go to the first list, and then I check if every single element from the first list is in the second list. And if this is the case, I append it to my thing. There's a nice what's called the quadratic algorithm, because you see this will increase quite a bit is the size of the thing. So both in F and G are on both. If you look at this here, F is look at F and G started here, they are on both. So that's not the best solution. Python is easier. So now if you use sets in Python, it's not only much faster, as we will see in a minute, it's also shorter. So instead of writing this loop, you just say intersection. Yeah? So intersection is doing exactly like what this is doing, but there's only one method call, intersection, and then you get the same result without writing this 4 lines. So that I think is a good trade-off for me. So you trade 4 lines against 1, and you get much faster just by using sets. And then I just put it in the function here for timing purposes. You see now I have these 2 lists, and have this here with a timer here to measure what I just did, how long it takes to do this. And then I call intersect list. You see how long it takes here, and I do the same thing for sets. I do sets, and then I check this in sets, and you see if you run the time, it's shorter for 10 already, yeah? But the result is the same. Now if I do a comparison of both of them, the same thing again, same procedure. I use my first function, my second function, and I get the times and the results. I just make sure the results are the same. And then I just create a ratio and I do a loop again. It seems the same pattern, and you see now it increases if you do this intersection. If it's small, you see difference on the big, factor of 2.75, and then it's going up. You see it's going up, factor of close to 100, factor of close to 1600, 19,000, and so on. And this keeps going, and it's very big. It's a very, very big difference just by using the built-in sets, which gives you so many nice features. So this one makes it, most of the time makes it also worthwhile to convert the list to a set, because this can be very long run times if you do this. So it's very easy. You just have to know that there are sets, and they have a lot of methods, and that can be very helpful to work with. And you get the algorithm for free. You don't have to think about how to implement this one. You could do the same thing with dictionaries, pretty much. If you write a loop of dictionaries, it would be very similar in speed, but sets are even more convenient because they have this intersection method already. Okay, another one, list versus DAG. So there's a few data structures in Python that are not standard, and they can be useful. I would like to introduce 2 of them. DAG and this is default picked, and they can be useful for some purposes. They are helpful. They make more elegant algorithms, and for some applications they are faster. They are not always faster. There's always a problem. You also need to measure if they are faster, because the speed very often depends on the dimensions of how big your problem is. It might be different for a small and a big problem, but it's fast. You will see this in a minute. So I have this. I use this decorator profile speed. Did you look at it? No, we have to look at it first to see how this is in measuring. So this is just another tool I wrote using the same. Did you use it? Did you look at this? No, it's a bit different, but also use a decorator. So it's the same approach as we had before. We use a dictionary to store our results, and we write a decorator that takes a function, and we write this function that use functional reps that we're going to replace our original function, and this takes just the arguments. The same thing we had before, and now we take a timer in the beginning. This timestamp, a timestamp, and we know when it started, and then we try to return the result of our function, and the end we calculate the runtime. And we store the whole thing in a dictionary, and we use our keystones here to have times and keystones. Yeah, pi stones, kilo pi stones, sorry, kilo pi stones, but we have here we just return this function. This is very similar in approach, and instead of doing this explicitly as I did before, just to show, we use this profile, this decorator, to measure the runtime of our code. Okay, so we do this, and now I can just go in and decorate my function. So there's a module, and there's a function, and I just have this remove from list. So we put in a list, and a start and an end, and let's just assign an empty list to this. So if you do this in Python, it's the same thing as deleting. You're deleting a whole range, say, okay, I have a list with 100 elements, and start end, you delete this part. That's one way of doing it. The other function would be using this DAG. So this is the other function, and instead of giving a, we have imported, we use a DAG, which is double-ended list, and we give it a start and an end. And now, this thing is, I will show in a minute, you can rotate. So I rotate it around the rotate. Let's look at this first down here, how it works. So we have a list, yeah, a list like this, from 0 to 9, and if I assign the 2 and 3 two elements, yeah, the last one is excluded, so the 2 and 3 are missing here. You see? Because I have assigned an empty list. And now if you use a DAG, which I import here, and the DAG looks like this, and if I rotate it, you see it's rotated around. You have it like this, and it's like an endless band, you just move it around. Yeah? So this way and this way. That means, and this one you can, lists are optimized to be, you do something from the end. This one you can do something from, just to rotate it around. And then you use pop. You see this pop? I can just pop off things, throw them out. Yeah? So this is list, I have to go inside the list, I have to rebuild the whole list, and here just, I can rotate it around and pop it off. And this, if you do this, it can be more efficient. So you have pop it off, you see now it's the same thing as pop off, just throw things out. And I do this here, I move it, rotate it around to -n, then I use pop so many times, and then I rotate it back. So even if I do so much, if I run this function, you see, now I create a list with 1 million elements. Now out of this list, I create a stack, my back here, and then I say, okay, I would like to remove the elements 100 to 105. And I just call my two functions. Yeah? And then I look at my profile speed. And if you look at the profile speed, you see this is you see this is a dictionary. I just use a key. The list time is this one, and the from DAG is this one. Much smaller, so it's difficult to look at it. Just we compute that. You see the factor of 66 difference. That's quite substantial. There's nearly 2 orders of magnitude difference, and nearly 3 orders of magnitude difference between those two ones. Even though I do have to turn around and call pop 5 times and move it back, it's still faster than doing it with the list. But this is only true for our example where we remove elements 100 to 105, so only 5 elements, 104 included. If I do more, so if I say I would like to remove 100 to 1000, so it's 999 I'm removing, our gain is much smaller. If I want to remove even more, now I remove 100 to 10,000, so it's 9,900. Here we use the 900, there's more, and now this DAG is not as good anymore. Because you have to do too many pops. Yeah? So it depends very much on your problem. So the DAG can be a good thing, so really 66 times faster is not too bad, isn't it? But if your data change and the structure, then it might not be good anymore. So if you develop these algorithms, you have to test it for different kind of data. You might get different results. It might not be obvious in the beginning. If you test always with small data sets, you might be surprised how they scale later on. Or you have different ranges. So actually we use the same data set, we use 1 million elements, but we use different range what we're going to delete. Yeah? So we don't make it actually bigger, we just delete the different size. And we still get some different results. So this sometimes can be surprising how things behave if you change the data. So if you do performance measurements, the one thing out of it, you have to measure this with a reasonable number of scenarios that you might expect. Okay, another built-in data structure is a default dict. Default dict also comes from the collections module. So the collections module has some interesting data structures that are not that common, but for some special purposes they can be useful. So let's do this standard example counting the number of letters in the sentence. So how many E's, how many A's, how many whatever. Here you can use this with standard in Python, and the typical approach would be using a dictionary, going through all the letters in S here, which I call key, and I use set default. So set default is a Python dictionary method which is doing several things. It's actually, let's do set default. That's maybe interesting, maybe not so much known. If you have a dictionary that looks like this, so it's always a very simple dictionary. Yeah, that looks like this. Now I can access this dictionary, and I can say, in this dictionary I would like to have A. Get this A. But I could also say set default A, which would give me the same result. So it's a good question why I'm going to do this. If instead of using A I use X, I get an exception here. Yeah? If I use X here, I can input some kind of default value if you like to. So I just provide a default value here. And now if I do this one, there's no exception. I get returned the 999, and my dictionary has changed because that's why it's called set default, that's the default value. That's a standard Python feature. I covered all my beginner's courses, but maybe not that much known. So that's a very interesting thing. So it has, instead of using try or check if it's inside, you use set default immediately instead of default. So that's built in Python. Let's go back to our set default. So that's what I'm doing here. So I set default the key. If it's not in there, I set a 0. And then I increment it. So I set a 0 first if it's not there, and then I increment it anyway. So if the first occurrence is 1, the second occurrence is 2, and so on. And then if I print it, as printed a little strange here, you see the space is there 7 times, the dot is there once, the capital S once, the A is 3, and so on. That's the thing it's doing. Good. Now Python has this default dict. So it's very similar. This is called set default, this is also default. It's doing a simple thing. And what you do actually here, you use collections and you use default dict. And default dict takes a constructor. So why I construct int? Actually, if you use int in Python, everything is an object. You make an instance of int because you can say int, and you get back a 0. That's actually what set default is doing, is generating 0 as default. It's nothing there. It's just using this called the function. You could supply your own function, but you use a built-in int. So you go back, and then you just set default. And now we can just do something like this. So we say plus equals 1, and if the key is not there, it sets the default as 0 as beginning. So we don't have to check any if or anything else. You just can go over it, and if it's not there, it just puts a 0. You can do the same thing with this or something else. And then the result is the same. It looks a bit different with default dict, and it's not written like this, because Python understands it differently, but the result is the same. The A is there 3 times. So it's nice. Yeah? It's not so much work because you have to import this module and you have to, yeah. So if you compare the amount of lines, it's just one extra line here. So pretty much the same, but you have to compare the import the module. But if you do now some speed testing, I use my profile decorator again here and run it through, and then use just the algorithm from above, just put it in a function. It's the same thing, nothing new. Then I run it and I compare it, and it gets a bit faster. So it's not really impressive here. Depends a little bit on the size, what you're doing, and also maybe the version you're using, and it might be a bit faster. So it's just something. Sometimes you can try things out. If you don't know it's getting faster. If you use different sizes, and of course it's small here. So if you use a different data sizes, like I use a million A's now, do the same thing, then the factor is 2.5 or 6. Yeah. So that's something that might be worthwhile to explore. The standard example from the Python for this thing, the Python documentation, some library communications, you have this dictionary with colors here and numbers on the side, yeah, over here, and you want to measure how many times they are there, and this is a standard example. Check there, and you can do the standard example. Standard example again. Yeah, this grouping by where you can let's go to the group by function uses default dict, and you just go through key value for data and for every thing you append it. So you append it instead of adding it, because you use a list as a default. So if it's not there, it will be an empty list, and you can just append to an empty list and append things and put this key. And there the key is the first one, so the key is that's a key, and this is a number we appended, and you see what's happening. And just compare it and see, this one doesn't really help, it's not faster in this case, because the data is too small. It's just a counter example here. It's not faster in this case. The handout handout is generated a different computer here, so this one has 1.8, so it's different. Okay, everything's right here, but I just copied it here. So I don't get anything here. This is different operating system, different computer, so you have the different results, but it's still in the same range. If I make it bigger, see if I do make it bigger and use the same function, then I get a different result. So one conclusion is this performance depends very much on the size of the data, and you really have to try it. And some data structures you can get a lot, like sets. You can get many orders of magnitude. Here, if you use a dictionary versus default dict, you can gain a factor of 2, maybe 3, depending on your data. Okay, let's look at this a little bit more systematically. So I have to go down here a little bit. There's no scroll. I will reach the page. I can go to the page directly. Okay, this is the handout, and I have assembled a table, what's called the big O notation. What we talked about is pretty much the big O notation, so the runtime behavior, depending on the size of the data. So there's one called O1, and that's what we have when we do, like our set, search in our set, or search in the keys of dictionary, or get the length of a list. It doesn't matter how big the data structure is, it takes the same amount of time, pretty much. So we don't talk about the factor of 2, we talk about order of magnitude. And then there's a linear one. This would be if you search to a list, it's linear. So if the list is 10 times as big, it takes about 10 times as long. And then typically for sorting, it's n log n. So it's not as bad as quadratic, but it's more than linear. So that's usually how you describe sorting algorithms with Python. And the quadratic one we saw already, this was our nested loop. So this loop for looking both is a nested one. That can be very long, and then everything bigger that might take very long. So if it's the cubic time here, so it's a nested loop, it's 2 nested loops. Yeah? And then factorial is even bigger than it's growing. This is this famous traveling cells, no problem about it. It takes even much longer. So those kind of things you can look at it, and if you run this just for very small increasing numbers, this one takes ages, takes very long. And this is just when you talk about it, and usually when you talk about it, you talk only about the order of magnitude. So there might be some constant factors connected here, but you usually don't express them. You just say that's linear. If it's 3 times or 5 times faster, that's usually not counted for as a linear factor. So then you have the if you look at those things, I have in my notebook here. Again, I use my profiling function and have a few examples for this different kind of things. So now use a list, and I do the thing you should never do. You insert 0 all the time. So if you want to have a list, you want to put something in the first place. You always do insert 0 here. It puts it in the first place. Here I do it differently. I always append, and when I'm done, I just reverse the list. The result outcome is the same. It's just one more line here. This line is the reverse. But if I compare both of them, again, they're both decorated. I do just can put them in here and have a comparing function which creates two two functions here. And I look at my result, and I do it again for different sizes here. And then you see if it's small, then the insert doesn't have any overhead, but then it's getting bigger. And you see, I'm not sure about this time I had to close my computer to this number, but it's a very big number anyway. Yeah, but it's increasing. So this insert 0 is also one of the anti-pattern in Python you shouldn't do. Because every time you do this, we have to rebuild the whole dictionary, the whole list. And if you do append, then you saw this graph is always appending at the end. So that's one of those anti-patterns, and you can see how many times it's doing those things here. Yeah. The second one it takes is square. Then you compare with how many times longer this is, pretty much how much more effort you have to do. You can calculate this also. Okay, this is one. So never do insert 0, always use append and use reverse. And then what I'm doing now here, probably have the same function. Might have a copy here. Which one I will compare it? Just a minute, I have to check myself what I'm doing. Use list, use O1. Use list, this is the reverse. So I'm comparing the ON O1 comparison here, and here I'm comparing the use list one, this is this one. I just take the list and make a list out of it, or represent reverse. Yeah. Okay, let's continue. Yeah, this is just my example. We are the end of the example. So this is just my dictionary example here. I did before. Good. So this is some small things about algorithm, things in Python data structures. We only have 15 minutes left, so we should better keep going. You can go back here if you want to. The next topic, I have a few more topics that are related. As I said, there's some selection of things you can do. The next thing is caching. Caching is something you don't want to repeat yourself. If you do something once, you might be able to reuse your result. Let's look at caching. So I have a few examples. So no more interactive, now everything is in files. So in caching, I have a few modules, and I have, we can do deterministic caching but not deterministic caching. Let's look at the helper function first. This one is taken from this book from Tarek here, and this is just a function to generate a unique ID for a function. So it takes a function, the argument here, and here I just take the module. So the function has a attribute module and a name, This is part of the key, and then I go through the arguments and I convert all positional arguments into a list of arguments and all keyword arguments into a dictionary, a list of, to keep the order here, a list of key values as strings. So this should be uniquely identify a function. So you have the module, you have the function name, you have the signature here, or the positional, or the other ones. And I just put them together with these columns here, double columns. I put all the key, the positional, and the keyword arguments together as a string. This is just one way to generate a unique. There might be other ways of doing it, but this is just one way that's readable. You can see where it comes from. Okay, that's the first thing. And now we go to caching. So very often you need you tend to call the same function again with the same parameters, and you recalculate some results. And there might be a way to make it more efficient by caching, and you avoid recalculating things. And this is again we do cache deterministic. First we have the deterministic cache. So first thing we need our functools because we write a decorator again, so we use our decorator approach, and then uses get key, which just this generates this unique key, and then again in the cache here you use a cache that's located in at the module level. You could put the cache somewhere else, you could put it in the function, but we decided here to put it in the module level. And then we have this time this decorator is different because it has a parameterized decorator. We have yet another level of indentation here, and we have to have 3 defs in a row. A little bit intimidating maybe, but it's not too bad. So we we provide our get key function as before, but the user can give its own if needed. There's no problem. You can have your own function to generate a unique key, and you can use a different dictionary. So if you don't want to use dictionary, this one you can give it a dictionary. So it makes it like this is the parameters. Then we write this function that's taking the actual functions that are going to be replaced. It's doing nothing more than just containing the function that's replacing the function. And that's why we do our functional wraps again. So this part we had before, exactly like this, and this outer part is extra. We didn't see it. It's just to give the parameter to make it even more flexible. And then we do the following: we go to our get key function and generate the key first. First thing we have to generate the key, give the function the arguments, and then we go in this dictionary cache and try. If the key is in the cache, then we return it and we are done. We return the pre-calculated result. So the first time obviously is not going to work because it's empty. If there's a key error, that means the key is not in there, then we go on and call our function. This is supposed to be an expensive function, it takes long, because we do a lot of things. If it's a function that's done 1 + 1, it doesn't really matter, because our cache takes much longer to do all those things around to the actual function. But if it's a function that takes maybe seconds, then it's really worth it. And then we call our function, and then we have the result, and we just store the result and return the result. That's why I have this lines here, so we calculate it, store it here, and return it. And then we have to do this scaffolding to do this. So once we do this, now we can actually use our function. So now I have to really do it interactively, just to show you. So I have to say from optimizing this. I have to put it in what I put it in there. Caching. Import cache. Long. So cache. Hopefully this is working. Check code. Yeah, that's what we need inside. and then it might work. So now I can re-execute this. I don't have to. Yeah, now it's there. Everything wrong. And now I can cache a function. So let's define a function here. So I just say I have my function. I use my decorator. Decorator is cd dot, and now it comes here, which is my memorized deterministic. And just select this one. And I don't supply any parameters, but I still use a parentheses here. But I could supply my own getKey function, and I could supply my own dictionary if I want to do. I don't do this here. And then I define my function, so I have a very fancy function that adds A and B here. And I just return. And actually what I do in here, I just say, just a variation, print, doing something. Yeah. So now I have this function memorized, and now if I call it, 10 and 20, it returns 30, obviously. And if I call it again, this 10 and 20, yeah. So we get this 10 and 20. It gives me a back 30, but it doesn't print it again. So obviously the function hasn't been executed again, but I get the same result. Because that's what it's doing. It's going in here and goes in the dictionary and finds this key. And we can look at the key actually. We can look at this dictionary. You can say cd cache. This is this dictionary. And you look at the dictionary. You see that's the key generated. The name of the module is main. Yeah? And the function is add. And there's two positional arguments here. There's no keyword arguments. A little bit advantage if I call this function with keyword, I say keyword arguments, which is exactly the same. I cannot distinguish. See, it's still doing it. Now I have the cache. Now it contains a second function with a different signature. So it doesn't distinguish. No, it's not perfect. It doesn't figure out that it's the same function call. So you might be able to do it. I don't know, but you have to dig inside. But that's if you call it with a different signature. So then you have the different second function is doing the calculation again. But you see how it works. So there's nothing magic. You can see everything. You can look at the dictionary, and since it's a dictionary and it's a global space, if you want to, I can just delete something from the dictionary, and then it will recalculate it because it's in the dictionary. So I can clean the cache from outside. There would be the possibility you don't have to put the cache into the module. You could put the cache in here, in this function, the containing function, if you like it. But then you would be able to get to it from the outside. There's no reference to it. This would be possible also. But if you put it in the module, then you can clean it from because you just delete it. You go into delete this key here, then it's gone and it would be recalculated. Yeah, so this is the whole key, and this is a result here. Okay, but the problem is if you don't do this, this will always return the same result. If it's adding two numbers, that's fine, it shouldn't change. But there might be things that get outdated. So you want to have a little bit of variation, and this variation is non-deterministic cache. Non-deterministic cache. And it looks like this. It's very similar. The only thing here, we give it the age. So this one has a kind of a timeout. If the thing's getting too old, it will get deleted. And we do this by using our parameter age, setting to 0 here. Which, if it's 0, it doesn't do anything special. And then we have, but if we give a different number, then it will eventually throw out this key after a while. And that's what we do here. We have this notion of deprecation. We have deprecated. So the age is not 0, and we calculate. If our value age, which we need to store, see, we need to get two things. We get the value and the age of the value, how old it is. And then we just say, okay, this age that we get, plus this limit here, which is different from 0 because we check here. If this is less than the current time, then it's deprecated and we recalculate things. So if things are too old, they will be recalculated. If it's newer, they will be reused. So that's something, if you put this in, then your function will be cached, or the result of your function will be cached for a while, and if the age is too old, it will be thrown out and will be recalculated. So typical things for database access. So you don't want to go to the database all the time, but after so many seconds or minutes, you want to go again, because it might be outdated. This would be one of those things. This would be one way to do it. And again, this is a decorator. You can get in here, you can adapt it to your needs. So if you need something different a little bit, you can change things around. Yeah? So you can also not only make it only dependent on the age, make it dependent on the size, or make it dependent on some other criteria you want to. The name, maybe you have different times of living, how long things live, depending on what kind of object it is. Those criteria can be a bit long or a bit shorter. You could do this. You have to just figure out how to identify the objects and have different times, for instance. Factors or something like this. Okay, let's try it. So if we do this, so instead of importing, now I can just use this line here and import my non-deterministic cache. Yeah. Non-deterministic cache. Yeah. And for any non-deterministic or something. Okay. Seems like it works. Doesn't give me any error. But now I can just do the same thing. But so if I just redefine my function, and instead of CD I use ND here. And if I don't do anything special, then memorize non-deterministic. Yeah. And if I just do something like this, then now the second time it doesn't produce a loop. It won't change anything. But if I now still not, even after a while, it's still not doing it. But if I say here, age, it's 5 seconds. So I redefine this function and I call it. The first time it's doing something, the second time it's doing nothing, but now I wait more than 5 seconds. Yeah? And then this should be deprecated and it's doing it again. See the difference? So it's just the 5 seconds I have here. This is just a very simple scheme. So if you need a more complex scheme, it would be difficult to put it in and have maybe different criteria. This would be some simple caching, and you could also, instead of putting this in this dictionary, so if I don't want have this now in this dictionary, yeah, is located in this dictionary, but I say this is my cache is just a dictionary, and now I can use this my cache in this. But I copy this one. I just can put my cache as in this dictionary. I have to check what it's called. Storage. It's called storage. Yeah. And I can just say storage. This keyboard. I don't need to take care of it. Auto storage is my dictionary. MC. Yeah. So that's storage. And now I can call my add. MC. You see it's in there. And now since I have, yeah, so it's in there with this number. If I call it again, it's doing it again, and I call MC. Again, see it should be, it's a different time, it's a different timestamp. You see different timestamps recalculated in the meantime, because it was quoted in 5 seconds, so it uses a different timestamp. But now I have the dictionary, I can do things with the dictionary, I have friends the dictionary. So it's pretty versatile, you can move things around, back and forth in different directions. Okay, that's caching, some interesting techniques. Good. I have one more thing Now I would like to go to a numerically expensive example and show a few techniques you can use. There's more, but a few things you can do with it. Make things faster, especially to little numerical things. Let's look at the handout. So I have written yet another function to test speed. So just a little bit of variation, just especially for my purposes. I use time it here, and time it is usually what time it is doing. It has this plus time. This plus time evaluates the string, and that's what I'm doing now. I'm just, you see, I generate some Python source code on the fly here, depending. I just execute a new function myself with some parameter. Looks a bit strange. It's just some string replacement. I just put the function name here, is the name of the function, and the argument there. So we have to do importing before you do anything. Let's import the function, and this is the importing. You also need to set up namespace. It's just some helper to see that you can also do helper like this, and then the rest is just generating a table with results. There's nothing spectacular. It's just of course I call several functions. They all have the same signature, and then I make a table, and the fastest one is the first one, and the other ones are listed below. And the first one has a factor of 1, it's the fastest, and everything else is slower, has a number greater than 1, and if it's 2, it's twice as slow, and if it's 10, it's 10 times slower. So that's pretty much what this thing is doing. It's just a helper. But let's look at the example. The example is a missed example. Let's look at the example. So this is one of those examples you see often calculating pi. This Monte Carlo sign is very fancy, but it's actually pretty simple. So you have a circle, and you see this just a part of the circle. This is 0 is the center, and the radius is 1. And I show you only a quarter of the circle. Imagine this is a whole circle. And this is 1. You can draw a square with a length of 1 and 1. So now we have this one. And now, if you do some a little bit mathematics. So I have to make it bigger a bit. Move it over. So if you do some mathematics, then you say, okay, the area of this square is PR squared divided by 4, or 1/4 of the circle, and the area of this the circle. Yeah? The area of the square is r squared, and then you just put both both ratios here, this area to this area, put this in, and do some conversion. Then you end up saying pi equals 4 times the ratio of those areas. That's all. But now we don't know the ratio of both areas. As a surrogate, we take the number of points. So the assumption is if we have an unlimited number of points, then they will represent those areas. So there's no such thing as unlimited, just a big number. But if you get close to unlimited, then you really get pi. It's just a very inefficient method, but that's what we want. We want to just show how to. So let's say we don't have a chance to get a better algorithm in this case, but we need to improve how fast it goes. And you have to throw millions and millions of dots or arrows in here. And they all guaranteed, they hit in the square randomly, and some of them hit inside the circle. And if you find out how many are in the circle, then you can just have this replaced in the areas and you get pi. And that's what we're doing here. And we have a pure Python algorithm. Yeah. So it's a plain Python algorithm. And it looks like this. So it's very straightforward. So we just calculate it. We know the total number, which is this one. So we know the total number. Yeah, and then we start with a count inside of 0, and then we just go through all our totals, and we just calculate x and y. Yeah, x and y are these positions here. If you look at this graph, x and y, this is x somewhere between 0 and 1, and this is y somewhere between 0 and 1. Randomly, we use Python's built-in random module, and then we use just Pythagoras, so the square root of the squares of this x and y gives us a distance. Actually, since we're between 0 and 1, we wouldn't even need a square root, but we put it here just for sake of showing how this works. And then if this distance is less than 1, then we increment the count inside. Then eventually we just have this ratio between count inside and the total count, right? That's our formula we just had, and you get pi. And lo and behold, it comes up with a number that's close to pi if you put a big enough n in there. So if you run this one, you get it. This just now I just have this check here, down here, that's measuring pi and see how fast it goes. It's just I can just supply the name. So I have some tooling here, just apply the function name, it's calling the function and doing all this time measuring for me, with the displays the results in the table. So if I run this one, so if I go to the here and I run Python plain, yeah, then see it 3.14, it looks like pi and it takes so much time. There's no real comparison because only one. So now I would like to try to do a few fiddling through different variations of the function to try to make it faster and see to measure it. So, but all this, you make a thing. I try to automate the measurement so that things are easy to do. You really do it, and you compare this. Okay. So I have a few approaches here. This is the first pure Python one. The next one. I'm using the math module. So the math module has a function called hypod, which is doing exactly what I did, the square root of the square root of x and y. And I figured, if this is built in Python, in a sound library, that's very fast than doing it by hand. That's what I thought. And that's what I did here. I just replaced this 2 or 3 lines there with this one, and the rest of the algorithm is the same. And then I just import my plain pi in this Azure time and feed it through my thing. I just have to list it here and run it. And then I run it, and I was pretty surprised. Yeah, that actually it's faster here now. It's a bit faster, because I had versions where this is much slower. I don't know, because the thing is, this math module is using a different algorithm. Because if you look at the C source code in the CLib, then it's a pretty long algorithm because they cater for very big numbers. So big numbers that might overflow when you use the square, make it greater squares, but then you use the square root and make it small numbers again. So they have a different algorithm which is more complicated, but you can use big numbers for it. How do you know if you don't look at size? So you assume it's faster, but it's not. In this case, it's a bit faster. If you use a bigger number, you might get some different reading. I use 1.5, 1.6, but probably this is faster. So it changed. The handout I use a different. This one, some of this is generated on Windows, and there might be some difference depending what platform on. So this one's obviously the math one is faster with the same ratio here. Let's save the file. Yeah, it's the same ratio. And if you have a different platform, you might use a different CLib implementation here and there, and things might be different. So that's not that straightforward sometimes. The ratio is pretty stable. So here the math version is really faster. The one I printed here, the math version is slower. So maybe somebody, if you have downloaded the source code, maybe you can test on your machine this different operating system if you get different results. Or if you maybe test with a different Python version. You can test it with PyPy. See what PyPy is saying. And PyPy they're very similar, but they don't have a lot of difference. So PyPy is a plain version is a bit faster than the math version. Of course, PyPy has a just-in-time compiler, and probably they can get deeper inside the plain version than the math version or something. I'm not sure. It's like this, so they are very similar. There's not much difference here, but a little bit to reverse ratio is all. Good. So this was one approach, and I have a few more things. 25 minutes. Here, we looked at PyPy already. So PyPy, it's a Python 2.7 compatible replacement for Python. So PyPy is very, very conformant with Python 2.7. So pretty much everything you write in 2.7 should work with PyPy. They have a lot of tests that are passing, so they are very, very close to 2.7. And if you can see here the runtimes, that's PyPy, that's normal Python. Here is 3 seconds, and here the runtime is 0.6 seconds. So it's a factor of 5 faster. That's something you can expect with a function like this. So there's lots of numerics. So if you do a lot of loops and it takes a little bit longer, then PyPy you can gain quite. You can get up a order of magnitude speed depending on the problem. There might be a few things PyPy is a bit slower, but most of the tests they have, and most of the library things, PyPy is faster. And for numerical things, it's significantly faster. You don't do anything. So I didn't change a single line in the code. I just call PyPy instead of Python, and that's it. You're done. The disadvantages working with extension modules, there's a lot of things going on, but so far PyPy doesn't work with all the extension modules. So you have to do something special to work with extension modules that are written in C. But there's a lot of things going on in this field, and people are doing things. So PyPy is a very cheap method. If you have the chance to run your program to PyPy, you can get a lot of speed just using PyPy. Yeah, and PyPy is just doing just-in-time compilation. And usually it doesn't work if you have very short program runtimes. If the program runs only fractions per second, PyPy doesn't have any chance to do anything. It has to run longer. Because the JIT has to warm up, what they call it. The JIT is checking in the background what's happening, recording it, and then it's optimizing the code depending on information against the runtime. So if you do the same thing over and over again in big loops, then that's where PyPy can do something. That's what we're doing here. So we do 100,000 times or a million times the same thing, so PyPy can improve things. So there's PyPy tutorials. I don't want to go into much detail. You can also optimize the PyPy, and you can go with the things. There's some optimization tools you can look inside, and you can tweak your algorithms and do things like this. But the cheapest thing is just use PyPy, and it should run. You shouldn't have a big problem getting programs to run only if you start using attention. So the whole standard library is implemented in PyPy. Everything is there. It works. And only if you use third-party libraries and they use C, then there's a website that shows you which one is working, which one is not working. Some of them work, some of them don't. So that might be the problem. And PyPy folks, they work on Python 3 support. They can donate some money, they ask for money. Because people have to work on it longer than just in their spare time. And they're porting it to Python 3. And there might be a Python 3 version in the near future, and then you can use PyPy. So it's an interesting approach. If you don't use PyPy, if you still use Python 2.6, so I know quite a few people, like if you work with Red Hat, it's still with Python 2.6. And you work on Win32 and 32-bit platforms, then you use Psycho. Psycho is a project also written by Armin Rigo, which is a lot of things from Psycho went into PyPy. So Psycho is not developed anymore, as far as I know, but if you still have old code and you might use Psycho, and using Psycho is very easy. You just import it. So I don't have 2.6 here actually, and it's 64-bit anyway, so I cannot show you. Just want to show you it might be interesting if you have to work with some legacy code, you can use Psycho. It's a very easy way of doing things. Somewhere? Yeah. So this is Psycho, and so it's kind of old, but it's cheap. The only thing you want to do, you have to import Psycho and say full, and it's doing a full optimization. That's it. You get the same benefits as PyPy. The only thing you pay is memory. This thing might take a lot of memory, so you might run out of memory or have memory problems one way or the other. But you can also fine-tune the things. You can Psycho is. You can tell them you can either tell them to bind only specific functions, only this function, nothing else. That would be possible. Or you say profile, and he's going to only optimize the ones that take the most runtime. So it's doing profiling in the background and just optimizing. You can give a limit, the one that takes 80% of the runtime, or something like this. So that's something you can do. this cycle, and it's not much more than importing it, and then it's doing everything with your program in the background magically. You don't do anything special. You can also have a proxy, so you want to have a fast function, slow function. When you compare them, you get a proxy. So that's something you can do with cycle. As said, it's only for this old architecture, so it's something that doesn't have the future, obviously. Of course, all the effort goes to PyPy and to cycle. But if you happen to be on an old platform, there might be something you can do. Okay, then PyPy. So PyPy is also just I'm mentioning it. So if you run it, then you don't have to do anything special. It's just pure Python, and all the things you learned about Python you can apply to PyPy. This is that. The only thing, the difference you saw was about the string concatenation. It's not optimized if you don't translate PyPy with a special option. I don't know why they do it by default. There must be a reason to do this. Then you can make things faster. So you have a factor of 6 here, depending where you're working on, you can be faster, slow. Okay, I have 2 more approaches I want to show you. There are plenty more if you go into the field of extensions. NumPy. Who of you used NumPy before? Yeah, a few people. So NumPy is still the numerical package for Python. So if you work with numerics, Python is really slow. Of course, everything is an object, and if you add 2 integers to objects, there's a lot of overhead going on. And numeric is this package that helps you to work with numerical arrays. Then I just used it here to calculate pi. So I have a NumPy version of it. So NumPy is a big package, so you can spend easily a day talking about NumPy. So obviously it's just very short. So I import NumPy. It's a pretty big package. Import takes a second or 2. There's a lot of things going on there. So, and then I work with arrays. And the principle is NumPy. If you write a good NumPy program, you don't have any loops. You get rid of all the loops, and everything is written in terms of NumPy methods and function calls. No loops. If you write a loop and you switch back and forth between Python and NumPy a lot, it might get slower than writing in Python. So I had this thing with people that used NumPy, but they wrote 4 loops in Python. It was really slow, and it took me a while to understand what they wanted, and I replaced it with this indexing in Python, in NumPy, and it was a factor of 1,000 faster, even though they used NumPy. But this is a lot of overhead if you translate the Python object to NumPy back and forth all the time. It's very inefficient. So you want to get rid of loops. There are some new developments. There's also some tutorials here about NumPy. You might know about this. They solve this problem very nicely, but it's very new. It's just a few months or so really that you can use it for something. But NumPy still stays. So you use arrays. So that's what I'm doing here. I say rand total, and this one doesn't give me a number, it gives me a whole array. So if I say total, a million, it gives me a million random numbers. And this gives me also a million random numbers. Do you see? I keep them all in memory. The other one was just a loop and had just 2 numbers in memory at once. That's it. Here I have the whole array in memory. So I pay with memory and get speed. So that's a trade-off. That obviously means this doesn't scale. If it's too big, it doesn't work anymore because there's no enough memory. So if you use 100 million, then probably it's going to give you memory error. And then I can use, again, I use NumPy square root, x times x. And this x is a whole array here. It's not a number, but a whole array of things. So if I go here and say import NumPy, yeah, and I say NumPy random dot random dot what did I use? Rank. Rank is here. So if I just use rank, and then I say, okay, I would like to have 10. I get 10 random numbers. This array like this is a one-dimensional array. NumPy is designed for multi-dimensional arrays, so you can have multi-dimensional, makes it a bit more complicated, but very convenient. Work with arrays. So you have the random numbers, and if I give it the name, this is random numbers, and I have a second array, which is B, which is also random numbers. B, also random numbers. And then I can, oops, I did something wrong. Okay, random numbers, and now I can have A and B are random numbers, and I can say A plus B and get a new array which is the sum of my original random numbers. Yeah, A look like this, A look like this, and B look like this. If you look at the first number, 0.34 and 009 gives you this 0.43. So that's element-wise addition. So different lists you can compare the element-wise addition. So that's what we're doing all the time here. And now we do element-wise multiplication. So every element X is multiplied by itself, every Y is multiplied by itself. Then you get another one-dimensional array, which is add together, and then it's good. You see, you generate a lot of intermediate arrays here. If you write in the C, it's more efficient because you write only one loop. And then we have an array of distances, and then from this array of distances, you just take the ones that have their distances less than 1. And this gives you back a tuple, and the length of it gives you back a tuple, and the first one is the number of the one inside. So it's a little bit different thinking. So you use where, and then you have this ratio, you can do this. And then you use NumPy, and then you can run and see how long it takes. And if you run NumPy, then it's quite a bit faster than reaching normal Python. So it's a different, very different approach, and makes things faster, but you are limited by memory here. So you pay with memory, so you cannot get any faster and do things any better. So NumPy is a very big library. There's a lot of things you can do. And if you're familiar with NumPy, then that's no problem. If it's new, then it might not be for you because you have to learn quite a bit how this works, unless you have other uses for this also. So if you put it in, then you should see the difference. Good. So I have one more approach because we only have 15 minutes left. This is using multiple CPUs with multiprocessing. So far, everything we did was in one CPU. And Python itself has what's called a general interpreter lock. So even if you use threads, you're running on one CPU, pretty much. Yeah, because Python is just currently giving everything up to the operating system, but it doesn't. You don't get anything if you use threads. You don't get any faster. You probably get slower if you use CPU-intensive things. If you do input-output, then threads are good because then you can gain something. But if you use CPU-intensive thing as we do here, threads is not the way to go because you don't gain anything. You can test that it will be slow. If you want to do something with multiple CPUs, then the thing that's the closest is multiprocessing because it's built in. Starting from 2.6, it's built in. If you have an older version of Python, you need to import it as backported. So it should be there for all kind of current versions. So if I go to multiprocessing, I have several multiprocessing versions. So I just want to quickly introduce how multiprocessing works in general. So multiprocessing actually allows you to use multiple CPUs on a machine by starting different processes. And it takes care of all this communication with different processes for you. So the API is very similar to working with threads. So you can use a program that actually works with threads and replace it with multiprocessing with just a few changes, some different imports, and then you could use it. But in the background, it's calling different processes and using Tiggle in the background to move the data from your process to the other process back and forth. So this obviously allows you to use several CPUs and the power CPUs, but also, of course, you have to create a new process. So which is, especially if you use Windows, it's pretty expensive to create a new process. Here in POSIX systems, you can fork things, which are kind of okay, but if you make a new process in Windows, it's pretty expensive action. So you might have more overhead than you gain through this parallelism here. Let's look at the an example, how to do this in parallel. So you see here, I try to import something for multiprocessing. If it works, it's fine. Otherwise, import from processing. So if you have a version, old version of Python doesn't have multiprocessing, you can install it as processing, and this is a typical way. You just try to import, and if not, you try to import, but otherwise it didn't have. Yeah? And then you need random and time it. And now we need to set. If you work for multiple CPUs, you have to kind of chop your problem into sub-problems, otherwise it doesn't work. So no matter how good the compiler or whatever you use, you need this high-level approach. You need to chop your problem into sub-problems. You won't get around it, some way or the other. You use GPUs, whatever you do. The same thing here, and that's what we're doing now. And this problem is very nice because you can chop it in so many small problems as you want. Every row can be its own problem, no problem. And now we just have to, instead of calculating pi directly, we just say, we call this function count inside. So we stop here at the count inside, instead of calculating pi, we just return the count, that's all. And because this is a random number, so it doesn't matter, they're random numbers anyway. If I do this everything in one loop or do it in 10 different loops, it doesn't matter. One loop is a million elements or 10 loops is 100,000 each. The random numbers are random numbers, so they're supposed to be random, that's the whole purpose, then they're not dependent on each other. So that's a very nice, embarrassing parallel problem. And that's why I chose it. Otherwise, it can be pretty difficult. You might lose performance if you do parallel things. You see, even if it's embarrassing parallel, you might not gain so much doing it in parallel. So that's our algorithm. And now we do the parallel thing. So we have this, I call it count pi, which takes the total, just calling the count inside and divides by the total. And then I need a process. Now I need a few extra things in post. This is the one that runs on this different process. So you have every process running this thing, and then this count pi is taking them back together. And then this is my main function, and this is what we call the main decomposition. So I take my total and divide it by the process count. How many processes I run? So put it for every process. So if I have a million total throws and I have 4 processes, every process get 250,000. That's what it's doing here. That's what it's mathematics. And I do integer division here, floor division, and just it might not be evenly divisible. So I have some reminder on this. What I'm doing is just people get the reminder. So they have all pretty much the same. One have one or more or less than the other. But if you have 250,000, 250,001, it's pretty much still the same. So that's what I'm doing here, just take it apart. And then I use a list of processes. You see queues here. And then I make instances of this queue. So you use queues, so if you ever use threads, you should always use queues if possible, because it makes the programming threads easier. Don't try to avoid locking. If you can use global structures, use queues to send messages back and forth. That's what we're doing here. You need to, because there's no global structure. It's a different process, a different memory, so you need the queue. The queue sends the information over there, and that's what we created in process. And this process gets this function we just defined, and this is going to run the function for us. So this count inside. Every process gets this kind of function. This is function here, and all the processes are running this function for us and give it back to us. That's what it's doing here. And this is the argument, the queue, and the counter. The counter is the one that goes in here. This is our queue, and then we start the process. So if you work with threads, you know this is start. Or start. We started, and then we append. So obviously this one is asynchronous in one way or the other, because we start, we can keep going. It doesn't block, otherwise it would define the purpose. Yeah, because you have to start all of them, and you append them, and then here this is blocking, because now we're doing everything, and I use get to get a result. So this is a very similar pattern you will see in all kind of asynchronous or parallel, whatever things. You have to get all the things going, you work in the background, and then you get the result back. And and here this get is blocking away, still it comes back. So there's no security. If one of the things dies and doesn't give a result, it's going to wait forever probably, or something like this. So you would need to make it more stable. But from the principle works, I get a result back, and it just runs through here with a generator expression to kind of generate the sum from all these different processes. So it's a little bit overhead, you see, but it's very similar. Whatever you do is a very similar pattern. And then at the end, I put everything together. I use join to finish. Actually, I use get ready, so but join to wait for the process to finish, and then return the thing. So that's what you can do. And if you run this one, and now I just have a test function that runs in this one process and several processes, and you might be disappointed a bit. how good it performs, because yeah. Yeah, one time I said, of course you added something on a function. One time. One time. I don't know how this happened. Yeah. Probably some auto replacer didn't pay attention or something, I'm not sure. Yeah, so you see, if you look at the time, one process takes 0.008 and 2 is much, much slower. So for small counts, the overhead creating the process is very big. So you don't gain, not you gain anything, you lose a lot using this thing. So you have to be careful what you're going to do. If you start increasing the number, what you're doing here, so now we have, it's 1,000, yeah? So if I use 1 million, then now it's not too bad. It's still slower, but the ratio is not near as bad. But the diff is, I will have the ratio 1.5 and the diff here. And if we go even higher, starting at like maybe another one, then somewhere things getting faster. So you can use multiprocessing for some things. It's very useful, but things have to be parallel for quite a while, and if they're not, you might not gain much. So this time it's faster, isn't it? Is it faster? Yeah. Yeah, the runtime 5 seconds compared to 7.6 seconds. This is also fast already. Yeah, already so it's a bit faster here. 1.5, 1.5. It seems like the ratio. But if you add more processors, this just has hyperscaling. That's just the rule called hyperscaling. You don't even have a full 4-core, you will gain too much more performance. So this is hyperscaling. Of course, I have my experience. It doesn't really add too much. If you had an 8-core machine, you wouldn't gain too much unless you have to use a very big number. So of course, you have to start too many processes and distribute it and so on. So this parallel thing is not that easy. And even though maybe your next machine has 16 cores or something, and you want to use it, it's not really easy to do. And multiprocessing is one way. There might be more in the future, more things you can do. Okay, so you're pretty close. I have another version which is using the pool, which is a bit easier, but also multiprocessing, but it won't get any faster. So you don't have to use queues. You can use the pool if every worker is doing the same thing. So that's a thing, and you can combine things. So it is nothing new. So multiprocessing is what we have, and then you can use a pool which is things which is very similar. Just in case of doing threads, it's easier. You don't have to make it too complicated. Just use a pool. That's the difference here. These two lines are different. So you use a pool with workers. And then you say pool asynchronous, apply asynchronous, so you see obviously asynchronous call, and you go through it and start all the results, and then you just get the log and get it back. It's a bit easier, you don't have to generate a queue explicitly, you can get the results back immediately. This is if all the workers doing exactly the same as we have here, that's probably easier. If all the workers do different things, then you can add percentage queues. And you can also, of course, make every process work with NumPy and makes it faster, but in this case we don't gain a lot. So we're nearly done, so it's just about time. I don't want to run over. You'd like to ask questions. I have just a combination with NumPy, so just use NumPy there if you want to read through. It's one way of doing it. And then you see I have different versions here compared with different. You see how much more you can gain. Which one is the fastest, which one is the slowest. You see pretty big factors if you use 10,000, you use parallel things, you really boom here, that's very hard. And if you increase the number, you get better results. And once you have big numbers, then you get better results for those parallel versions. Okay, they have a table at the end here, and assembled a few methods, and 3 methods we talked about. If you haven't talked about, and actually there's a few new ones, so it's not even in the table. So if you would like to work with C extensions, which is one way to make things faster, then you have options. You can use Cython, which is a very nice mixture between Python and C. So we have actually have more than 1 day course. Cython is a very comprehensive package. You can do a lot of things with it. It's very nice. C types, interesting. C types you can use shared libraries that are written in any other language, C or whatever. And there's a multitude of options to do this extension things. So there's also, now you can use GPUs for some things. For some programs, GPUs are useful. And there's some bindings in Python, but it's a totally different topic. But this one you can gain maybe 2 orders of magnitude if you have the right problem and you're able to use the potential power of GPUs. For instance, that's not that easy, but potentially it can be 2 orders of magnitude faster. GPUs in there. Okay, good. We are right on time. I have everybody should fill the tutorial evaluation. So there are some, at the side there are some QR codes there, and some links. So I don't have the links now to show you. And everybody should go there and fill the tutorial. I don't know if you can find it on the website. Fill the tutorial evaluation. Please do so. People ask me they want to have feedback. How we can improve the tutorials, what was good, what was not so good. Those kind of things would be nice if you fill this thing. So I have to check. So I will find the link. But it's all written at the wall. There's a link to the tutorials, the survey thing to fill things out. So this concludes our short excursion to the optimization world. I hope you learned something out of it. So you see, the first thing you have to measure, and then you might be able to do something about it. And there are a lot of tools out there. But the thing is, no matter how good the tool is, you probably have to tweak them a little bit to do exactly what you want. And I hope I gave you a few hints how to do this. Decorators is one of them. And there's a lot of things to make things really fast, but it depends very much on your problem. And there's no strict rule. The only thing you have to try it out. That's pretty much my message. And try to experiment, try to measure, and make your program getting faster. So I will be around for the whole conference, so if you want to talk to me, you're welcome. So of course the next one I'm going to enjoy sitting in the toilet myself, listening to other people explaining. Thank you very much.